as Roman said, I'm Matt Newville. I work for the Center for Radiation Sources. I run beamlines at the University of Chicago and the APS. And I've been doing XAS for a while. Okay, so start this morning with an introduction to XAS. Now, I know that many of you here, or at least some of the people I saw, are very familiar with XAS. So this will be a quick and sort of run through the basics of XAS. And then I'll give a demonstration of sort of data reduction, a little bit of Zane's analysis using the Larch XAS Viewer GUI tool. And then I'll give a presentation just on using FEF and doing XAS analysis, shell by shell fitting, it's often called, where you really model the extended XAS. And then I'll give a demo of that using sort of command line and scripting tools. Again, the materials are here. And I'll try to stop in the middle of this talk, and then at the end for questions. I'll see if I could figure out how to see all the questions. Okay, let's get started. X-ray absorption spectroscopy includes XAS, Zane's, XAS, all these different acronyms. Some for X-ray absorption and spectroscopy, sometimes with the word fine structure in them. These all discuss and are concerned with the energies just above the threshold energy for an atom, and that the X-ray absorption coefficient is modulated by the neighboring atoms around that absorbing atom. So here's the iron K-edge XAS for iron oxide, which we'll beat to death in this morning. Characteristics of XAS, you probably all know this, but I'll just go over this for completeness, are that it's a local probe. It probes the local structure, the near neighbor atoms, the molecular unit around the absorbing atom, and not the crystal structure. It's very sensitive to oxidation state or valence, and it can apply to basically any element. You can use it at fairly low concentrations. There are actually fairly minimal sample requirements, although you can, so that means that you can do very fancy things with it, like time-resolved work if and when necessary. The basic physics is the photoelectric effect. So X-rays are absorbed. Actually, most light is absorbed by the photoelectric effect, certainly high-energy light like X-rays. In the photoelectric effect, a photon of light is absorbed by an atom by one of its core electrons absorbing that energy and making a hole in a deep level. So X-ray comes in, a 1s or K-shell electron is destroyed, and energy from the X-ray is given to the hole, and perhaps a photoelectron is created if there's excess energy. So we say that the atom is left in an excited state because one of the core electrons is empty. One of the core electron levels is empty. There's a hole, and the excess energy is given to a photoelectron, which travels away from that absorbing atom. Of course, this is actually what Einstein received the Nobel Prize for describing. I always like to say that there are actually two related phenomena to X-ray absorption that we need to think about when we're doing practical measurements, and not so much for the theoretical aspects, but for any actual experimental work. You need to think about X-ray fluorescence. So once that hole is created, another level, a higher level, can drop down to that level and fill that hole and give off a characteristic X-ray with the difference in energy between the two levels. That could give you K alpha, K beta, and that's X-ray fluorescence. So all of X-ray fluorescence analysis is sending in an X-ray or electron to kick out one of those core electrons, and then visualize or measuring the emitted energies coming off of those characteristic energies from those atoms. In addition to X-ray fluorescence, there's also Auger electrons that can happen. So that core hole could be filled by from a higher shell falling into that level and preserving momentum, another electron being ejected from the atom. Those two effects are sort of the complementary effects of X-ray absorption. And they're more useful for identifying an atom, with X-ray absorption, you've already selected the atom that does the absorption. So like with most light, X-rays are absorbed, and the way we describe that absorption is by the intensity drop as it travels through a material. So the X-ray absorption coefficient is the exponential drop in intensity as light passes through a material. What's interesting for X-rays and why it's useful for in many medical and many applications is that absorption coefficient mu depends strongly, very strongly, on the energy of the X-ray and on the atomic number of the atom doing the absorption. It will also depend on the density as well. But it goes as z to the fourth power and energy to the -3 power. So here are the absorption coefficients on a log scale, actually on a log scale for energies from 1 to 100 keV and values that span 5 orders of magnitude. And you can see that the absorption for oxygen, iron, cadmium, lead here vary quite a bit. So so that's why you can image your hand with X-rays, because the oxygen and carbon in your flesh don't absorb very many X-rays. The calcium in your bone absorbs a lot of X-rays, and the gold in your ring absorbs all of the X-rays. So that can be useful for imaging, and it's important to understand for many practical and experimental applications. But what we're interested in with XAFs is these sharp jumps in the X-ray absorption coefficient that happen at discrete energy. Those are the core level electron or core level electron binding energies. And when you go across one of those, the absorption jumps dramatically because now that new electron level can participate in the absorption. And this is what we're most interested in, because if we zoom in on that level, say for iron, here's the iron K edge at 7,100 electron volts or so, there's a sharp step, and we also see these oscillations. So we're going to take that absorption coefficient and make it differential. We'll say there's a sort of static component, and then there's a differential component or a response function, a susceptibility, if you will. XAFs, and that's the XAFs, the parts of the absorption coefficient that are the oscillations, the non-smooth parts. We can rewrite that as mu minus some like flat mu0. So we have a bare atom absorption, or a mu0, which would be the theoretical or idealized absorption of an atom without any neighboring atoms. And then we'll divide by the edge step, just so that we have some unit of normalization. So here is then those oscillations isolated from a smooth background. We'll go into much more detail about how we do this process later on. As we'll see, XAFs is an interference effect of the photoelectron that gets emitted from the atom. So what we become interested in when we think about understanding and modeling the XAFs is the wave number of the photoelectron. So that's the square root of the energy of the photoelectron. So the square root of the energy above absorption, with some fundamental constants included, mass and electron and Planck's constant. So we use this value K as the wave number, because we will see that the oscillations in the XAFs are periodic in that wave number. So we'll also often multiply, we'll just amplify the XAF, so we'll multiply by K squared, and here then is that same data. And you see that's oscillatory, so that implies, and the way that XAFs was first understood now 50 years ago, was if it oscillates, there's an oscillating signal, you can do a Fourier transform. If you do a Fourier transform of that signal, you see an amplitude plot that looks something like this. And this peak here in the Fourier transform comes from the iron-oxygen scattering vapor. And this peak here comes from the iron-iron. So for iron oxide, which is iron surrounded by oxygen and then by iron. See immediately that you can detect and measure information about the neighboring atom, maybe the second neighbor, and then some further out neighbors. Now, there are some things about this function that we'll go into more detail about, but that's almost a radial distribution function or a pair distribution function. It's not quite, and we'll get to that in a second. Actually, we can get to that right now. To model the XAFs, we have an XAFs equation. We'll go through this, how we get this equation, because I think it helps you better understand the process, and so then that helps you better think about how to model your data. We have an XAFs equation that is a little bit more complicated than Bragg's law, or a little bit more complicated than a linear regression analysis that might be used for machine learning things. It's a little bit more complicated than that, but it's not too complicated. We have some amplitude terms, and we have a series of sine waves. So we have sine over kr and a sum of those. So we have functions here. I've called them f and delta. The literature will often give them different names. That are photoelectron scattering properties for the scattering or neighboring atoms, the iron neighbor or the oxygen neighbor from the absorbing atom. And there's also a lambda, which is how far a photoelectron can go before it gets lost. And if we know these properties, you know those properties, you see that you could, at least in principle, determine r, the distance to the neighboring atom, the coordination number, n, to the neighboring atom, and something that I've included here as a mean square disorder of the neighboring atom. And that is effectively the statistics we need, the values we need to determine the radial distribution function or the local structure around the absorbing atom. So we'll also see that f and delta depend on the atomic number of the scattering atom. So there is some sensitivity. We can distinguish between iron oxygen scattering and iron scattering, as we'll see, and we might even get to later this afternoon. It's challenging to get that to high precision, but we can see it sort of rows of the periodic table easily. Okay, so let's work out why that equation is the way it is. This will be a quick tour of quantum mechanics and hand-waving quantum mechanics. I used to be a physicist, I'm no longer. So this is hand-waving quantum mechanics. If we think about that, an atom and that absorption process, that Einstein absorption photoelectric cross-section, X-ray comes in, the deep core level gets destroyed, and a photoelectron gets created. And the photoelectron has a wavelength or a wave number that's 1 over the square root of its excess energy above the continuum. So again, we see as the X-ray energy increases, at some level, we can now destroy this core level, and so we get an increase in absorption. That's the absorption edge, and then it continues to decay as the E over cubed. So below this 1s energy, below the edge, we see very little absorption because there's no available state for that core level to transition to. All of the valence states below the continuum are filled. There's no empty states there's no empty states to which it can go. So once the energy level becomes higher than its core level binding energy, then there are lots of states it can go into, and so you see a huge jump in absorption. So that's basically to hammer home this idea that in order for there to be absorption, there has to be a state for that photoelectron to transition into. And that's so edge coming from the core level binding energy and the absorption threshold, the density of states for that photoelectron to go into. And that depends on which quantum number it is. So 1s has to go to p. So this is the p density of states. I'm sure that the theoretical calculations described will go into much more detail of that. Now, what happens when we put a neighbor next to the atom? Well, that photoelectron can scatter from the electron density of the neighboring atom of this. So you can call it the neighboring atom. We also call it the scattering atom. That's the neighbor that scatters the photoelectron. And that photoelectron, that scattered photoelectron, can make it back to the absorbing atom itself. So it can backscatter is often what it's called. So as you can see, as I've drawn here in a cartoon, that then backscatters, and its amplitude varies at the core level. Its amplitude is varying just because the energy and so wavelength are varied. So now the photoelectron absorption will have these oscillations in it, because whether this electron can go into that state at all is modulated by the fact that it wants to backscatter, and so put some electron density there, thereby decreasing, or if it's negative, increasing the density of states. It all seems like quantum mechanic magic, but that's how it works. So the XAS oscillations are due to the interference of that outgoing photoelectron with the photoelectron scattered by the neighboring atom. Okay, so if we go back to our definition of mu being the a bare atom part and then a differential part on top of that, we can do a simple analysis, a simple description, a heuristic description to understand the XAS ought to go. So we'll use Fermi's golden rule, which is what you use for any transition. That is, you have to go to a state. We go from one state, an initial state, into a final state. And we might have some operator that does a slight transition of the states. So for us, for absorbing an X-ray, the initial state is the core level having an electron and a photon existing. So that's the unperturbed state, the original state. We'll sort of ignore this interaction. There is a dipole rules, and that actually helps with the selection rules. We'll ignore that for now. And then there's a final state in which we have a photoelectron, and we have a hole in the core level. That's the final state. And all of the details that we see in mu come from that change in the final state. So we can work this out a little bit more mathematically. If we think about the final state being mostly, this is a slight change. This is a small change in perturbation. So we'll say the final state is mostly the original unaltered atom, and then a slight variation. So we can just work that out sort of as a Taylor series expansion, and you can see that we have the sort of Fermi's golden rule, the interaction with the bare atom being mu0, and the interaction or the overlap of the initial state with the change in the final state as giving the XAS. That also sort of makes sense with what I described earlier, that it's the change in the final state, the change in the photoelectron that changes the absorption. So again, our XAS, our chi, is approximately the overlap of the initial state and the change in final state. So what is our initial state? So this is a talk, so I can easily switch and make a lot of those assumptions. The initial state is just the core level. And so for a 1s, that's very nearly a delta function. So we'll just say that all of the core level interaction is a delta function at the origin, at the center of the iron absorbing atom. And the perturbation, the change, this delta F, is just the scattered portion of the photoelectron. So the photoelectron goes out, and part of it comes back. That scattered part, that's what's changed at the atom. So the chi is due exactly and only to that part of the photoelectron that makes it back to the central atom. It's the intensity of the amplitude of that wave function of the scattered photoelectron at the origin, overlapping the 1s electron. So now, with that idea, we can write out a simplified version of the equation. We'll write it out simple, and then we'll add all the bells and whistles. So if we think of the scattered photoelectron, or if we think of the photoelectron going out, it's a spherical wave. So we'll say it's just e to the IKR over KR. It's a sine wave going out. So the photoelectron leaves the atom, that's e to the IKR, and then it scatters. And I put in here some probably tricky math. There's an amplitude and a phase to that scattering, because we're a complex wave function. There's a real and imaginary part. There's an amplitude and a phase shift, and then it returns actually the same e to the IKR over KR, also as a spherical wave. So it decays as 1 over KR going out, and then the backscattered photoelectron also decays. So we can have 2 KRs in the equation. So we put that together, and we take the real and imaginary part, and we get this amplitude F of K divided by KR squared, and then times the sine of 2KR. The 2 comes from it going out and back. So we have 2R as the complementary value to the wave number K. So that's the XAS equation for a one scattering atom. Of course, we don't have one scattering atom. We don't even have one photon being absorbed. We have billions of them, actually more like trillions of them in many cases for modern synchrotrons. And so we have a number of neighbors for the atom. There might be some disorder in that distance distribution around R. And so we have a sum of over neighboring atoms and a range of distances that will model as sigma squared. In general, we would have a partial pair distribution function, and these kinds of things can be used for modeling XAS. It works very well. For today's talk, we'll mostly stick with the distribution of atoms around a shell is approximately Gaussian. So and sigma squared are all that describe and a distance r are all that describe the distance per distribution function. Okay, and now I think we're getting close to the time for questions. And now, if we look at those scattering amplitude and phase shifts, we can calculate these. We will calculate some of these. We can look at them as a function of k, our wave number, and we see that there's a plot here for oxygen, iron, and lead. And you see that at higher z, the F gets larger at high k. And for very heavy elements, there is pronounced structure. Actually, that structure is there for all of them. For lead, you see this pronounced dip and a strong resonance or anti-resonance. The phase is a little less obviously different, but actually those are big changes in phase shift too. And then there's this huge jump in the lead. So these can be used for understanding the atomic number that's doing the backscattering. So Z can usually be determined, I usually say, to within 5. If we have time at the end, I might show an example of that, or it's in the materials for this course. Ambitious. So you can definitely determine iron from oxygen, and you definitely cannot determine iron from manganese unless you work extremely hard. And once you've worked extremely hard, then you will find that you have to work extremely harder to distinguish iron from manganese. In any great detail. I often get asked if you can tell, say, iron from or oxygen from nitrogen, and my answer is typically no from extended XAFs, but I know that people use Zanes in calculations and should try to work that out better with Zanes or with analysis methods such as valence to core transitions, which can distinguish those ligands. Okay, so I'll go through the data reduction, and then we start on the demo of data reduction and work on doing some looking at real data. So data reduction, we need to convert the measurements we have from the beamline or from the source that we're using to a value of mu, and then we want to do the extraction to chi of k. So we're going to make those make mu. Which can be complicated, actually, depending on how complicated your beamline is using. Then we'll remove instrumentation backgrounds, and then we'll do the step of normalizing so that it goes from 0 to 1. We'll remove a smooth post-edge background, and then we'll select energies for E and convert to K-space. And we might do some Fourier filtering. Okay, so what you measure at your beamline is, for transmission XAFs, you might measure an intensity I0 that looks like this. There's often some little glitches in the energy or the intensity of the incident beam, and then a drop in intensity as you go across the edge for the transmission chamber or I chamber. So you need to turn that into mu by taking log of I over I1. Now, I'm going to stop here because this gets into the weeds. When we said I over I1, we meant the intensities, and these are counts in or even like voltages or currents from an ion chamber or from a detector. It turns out that if you have both using both ion chambers, or even most detectors, that the effect of that is not converting that to real intensities is not very big. But it means that our plot here of log of I0 over I1 or minus I over I0 has these values to go from 0.2 to 1.6, those values themselves aren't very meaningful. But the step there, the values are not meaningful because when you take the log, a multiplicative factor gives you a constant offset. These intensities or these voltages or currents that came out of our ion chamber might be scaled differently. We might have just amplified them differently. So these values by themselves aren't very meaningful, but the difference, that jump from 0.2 to about 1.2, means that the edge step is about one log unit of intensity. You want to make sure when you're doing transmission that you have a jump that's on the order of 1, that is to say somewhere between 0.2 and maybe 3. But once you get above 3 or 4, then you've absorbed all the X-rays, and it's not very efficient. And when you have a very low absorption, so the absorption is, say, 0.1, you haven't made a very thick sample, and the data quality might be worse. So the jump there is important, but the actual values are often not so important. Okay, so once we have that, then so this data set, like this is the same, this is probably just a different measure of iron oxide because these values are different. They go from like slightly -0. How can it be -0? Well, it's a log, so the values are just less when we take the when we divide them by each other. Take the different other. So we want to fit a pre-edge line. That's going to remove the other instrumentational effects, but also the absorption from lower energy edges. And then we want to extrapolate some sort of line to get the edge step so that we can divide that. So we can go get a normalized mu that goes from about 0 to about 1. When we're doing Zane's analysis, how good that normalization is can make a big difference if you're trying to do linear combination or principal component analysis. For extended XAFs, it's not a huge effect. It can affect, but it will affect the absolute value of the coordination number. So getting that right is important, but getting it right to 3 decimal places is as we will see. So the Zanes, we can interpret the Zanes. We'll come back to that in a second. And then we often look at the derivative. There's a value we'll need a value for the threshold energy for E0 to define K. And typically we don't know what that is, very high precision. So we take the maximum of the first derivative of mu of E. That can also go to what the energy calibration is for measurement, which can vary from beamline to beamline, at least a little bit. For iron, it's not unusual for energies to vary by 2 to 10 eV between beamlines, but a variation of 20 or 50 eV is quite a bit and unusual. So then we'll want to take this post-edge background. We'll want to remove this atomic mu0 background, and I'll talk about that in the demo. We don't have a measurement of this with an adjustable spline. We understand, or at least we think we understand, how to pick that spline, and I'll show you some examples of what can go wrong, what you want to do and what you want to not do. But because we're using just a mathematical smooth spline, it can be dangerous. So we have a lot of checks in place to make it less dangerous. Still, you can always cut yourself with the wrong side of a knife or the right side. So we want a spline that will match the low frequency components. We want it to be smooth. That's the fundamental understanding. So then we have chi of k extracted from that. Mu minus mu0 divided by the edge step. We set the edge step to 1 already, so it's just mu minus mu0. And then we might multiply by k squared, and we might then add, because it's oscillatory, we will do a Fourier transform, and so we might apply a window function just to multiply that spectra by this curve to reduce the ringing, just to better sample the portion of k space that we want to analyze and to remove this thing that was really the initial absorption threshold, the white line. And then when we do that Fourier transform, we get a plot like this, which is what I showed earlier. And so this is iron oxide, and you will notice immediately, because you're all good chemists or physicists, that the iron oxygen distance in iron oxide should be 2.14 or so. And the first peak here is at 1.6. So you could say, wow, you got it very, very wrong. XF doesn't work. But that's because we have this phase shift, delta. So we don't have sine of 2kr, we have sine of 2kr plus delta. So a phase shift of 0.5 is typical. In fact, I'm doing okay on time, I think, so I might even go back to that. Let me go back. Sorry. Here, that's what I wanted. If you look at this plot of delta, okay, they're all different, but they all start at 0, and then at about minus 20, a k of 20, they're all about minus 20. So they all have a slope of about minus 1. So if it's 2kr plus delta, and that delta is minus k, that gives a phase shift of half an angstrom. And it's all down, so it's all to lower R value. So it's 2k R times quantity R minus a half, roughly. I mean, you have to take into account that that's not real. That's not, that you can't do analysis like that, but that's why there is a half angstrom phase shift or half angstrom shift to lower, I should go back, stop, to lower distance. So the peak at 2.14 is an atom at 2.14 angstroms gives a peak at about 1.6. That's the half angstrom phase shift. That's typical. And then the Fourier transform is complex. So we need to consider not just the amplitude, which is typically plotted in what you'll see almost exclusively in the literature. Actually, there are oscillations, and we're going to fit oscillations. We're going to make sure we really calculate that and work with the data correctly, because these oscillations and where those the phase of that curve is important, and we'll use it for the modeling. Both real and imaginary. I usually show one or the other, and I go back and forth on which one I show, so it doesn't matter. They're not that distinct. Actually, they're out of phase they're out of phase from each other because the real part of the measurement is 0. So, okay, so it's not uncommon. It's not uncommon to see, but I would say it should be uncommon to see that people will try to isolate a shell and then back transform that. So they will, again, take this curve and multiply by a window and Fourier transform that back. So that is meant to be the isolated contribution of the XFs from the iron oxygen. I would say you don't need to do this. And I would also say, if you think you need to do this, you could get yourself in a lot of trouble doing this, because that dip there between those two peaks could be because the atoms, there are two separate atom shells, and it could be for some other reason, for a more complicated reason. So you might not be actually isolating a shell. You might just be doing a weird filtering of your data and then trying to model a portion of your data that you don't fully understand. So this can be dangerous. I recommend it, guys. Okay, so finally for the first part of this talk, I'll talk about XANES. I think a lot of you know this already, but XANES is the near edge structure. And again, because the absorption is all about what is the unoccupied, what are the lowest energy unoccupied states that are available for that 1s, we'll say, photo into, that can depend greatly on chemistry. So the poster childs for XANES analysis are chromium, where chromium-6 and chromium-3 are wildly different. This peak here in the chromium-6, the chromium-6 oxide is tetrahedral, so the P and D empty density of states for the chromium atom are very strong. The P density of states from the oxygens hybridize with the chromium D states, and you get this huge peak. Actually, you see it's a small peak for the chromium 3 plus. It's not 0, it's small, and then it becomes huge for the chromium 6 plus. For arsenic, for example, you can easily distinguish 3 plus from 5 plus. These are the dangerous and the not dangerous, actually, for chromium, right? So chromium 6, this is cancer causing, and this is more or less benign, if not actually useful biologically. So XANES measurement easily are one of the only ways to easily and unambiguously distinguish oxidation states. Other methods work too, but X-rays are quite good for that. For iron, or for all of the transition metals, there's also a wide variety of compounds and spectra that vary with local atomic structure or with chemistry, with the molecular units involved. So this can be used for fingerprinting and any linear analysis. So here in the unlike for the extended XAS, where we're modeling that photoelectron going out of decay, here it's often useful to just look at that as a spectroscopic method. So fingerprinting, or saying that there is some iron sulfide and there is some iron oxide 3+, or some ferrihydrite, hydride, say, in my sample. Just do a linear combination of those to get out a better understanding of the sample that I measure. And so we don't have actually the XAS equation would work for Zanes, but that sum has to go to infinity, so that's inconvenient. We don't have a simple equation for Zanes. And we can describe Zanes qualitatively and semi-quantitatively in terms of coordination chemistry and band structure and molecular orbitals, also multiple scattering. And both Josh and Fair and Yves will talk about that at great length, and maybe even the modeling will talk about that as well. And it's all a question of what electronic states can that photoelectron fill. So Zane's calculations are becoming, actually, they're now quite reliable. And they can help you interpret what the orbitals are and what the density of states are for the absorbing atom. So for Zanes, it's much simpler. It's a much larger signal. It's easier to measure than XAS. It's faster to measure. You can measure it differentially. You can measure it lots of different ways. So all of the advantages of XAS measurements are doubled, or a factor of 10 better for Zanes. And the interpretation from a linear spectroscopic analysis point of view is actually quite readily available, and you can use linear modeling methods. So all of these fancy machine learning methods can be used for modeling. And I would go into detail on some of that if we had more time. But Zane's modeling, that is ab initio calculations, can be quite complicated, but they're actually good enough to use. Okay, so more information. As Roman mentioned, there is an International X-ray Absorption Society. The webpage is xrayabsorption.org. You can also go to xas.org. There are a number of good books about XAS. I would encourage you to look for Introduction to XAS by Grant Bunker or XAS for Everyone by Scott Calvin. These are both excellent books to have just lying around. Actually, the Elements of Modern X-ray Physics book is also actually very good, and its description of XAS is quite good. Okay, so here I'm going to break for questions and then get ready for the data processing demo. I think this is also like a fine time to take a small break if that's necessary, but I'm happy to answer questions on any part of this or anything else coming up. So.
Hey, Matt. So there are a couple of more questions. One of them is, can you differentiate between sulfur and chlorine? And I believe it's about the higher shells, not the core atom.
So is hard. I think I would say from in extended XAS as the neighboring atom of extended XAS, I would say don't count on that happening. That would be extremely difficult to distinguish those two. There are other methods, so you could look at the Zanes. So you could look at the Zane spectra and see if you can distinguish sulfur from chlorine ligands. And you can look at, there are advanced emission spectroscopic methods, valence to core methods. These are advanced and can't work on every system, but they work on many of them quite good.
Okay, and I hope we answered the question. And the other one is, can you show an example of XAS data for a very sensitive concentration of 1 ppm, low concentrations? I'm not too sure if you have any examples. You are going through it in your demo, or?
I don't think I have any in my demo data of 1 ppm.
Okay.
Well, so I would say at my beamline and many beamlines, we measure Zanes and sometimes extended XAS at 10 to 50 ppm on a regular basis. It always matters what that other million ppm are. So you can do 10 ppm of iron in water or in a biological system, but you can't do 10 ppm of cobalt in iron metal.
In iron, yeah. Okay.
I don't think I have any data for that. So definitely, so I would say I would say for people who come to my beamline, my sort of standard boilerplate is 10 ppm we can do, Zanes for sure. We're trying to do Herfty at 10 ppm and maybe at 100 ppm we can definitely do some, maybe first shell extended XFs, and then to do better than first shell extended XFs, it's always like that's more about the sample and the beamline and the energy ranges and so on. So 100 ppm, there's hope. It's doable. 50 ppm, it's not out of the question. 10 ppm, it's challenging. And I would say that for like just for the biological and catalysis communities, those are actually probably a little bit lower than that because I'm mostly working with people who bring rock samples and they're interested, in copper, but the calcium is enormous. So the backgrounds are higher in rocks or arsenic and iron oxide, right? So it's doable at the 10th to 100th ppm.
Okay. The other question is, I kind of think that you will get to this when you are going through your demo and showing how Larch works, but they want to know how to choose proper K rate.
Yeah, okay. I'll try to say, right, proper.
Yeah.
Yeah, the answer is it's 2 or 3. That's the answer.
2 or 3.
Yeah, and proper. I don't know.
I don't know what that proper. Yeah.
This is now going to be a demo. I would invite you to follow along, but I just sort of have to say this with 100 people. That just like it's not for remote. It's just not going to work. So if you have questions about like it not working or something, I invite all 100 of you to send me emails or use the IPFM mailing list to ask questions about like how to get this to work, or if you have questions about this, I'll try to answer them all. I'm running beamlines too, so I'm fairly busy at times. But I don't think I can really spend time here getting it to work on your computer. Okay, so
just a thing before you start the next session. There are a couple of more questions. Maybe one of them is more related to this, so I'm going to ask here. The question is, in Zanes, when can I consider the photoelectron is in fact ejected from the atom instead of being promoted to unoccupied states?
That's an excellent question. Okay, so So the photoelectron, so one interpretation of this is the photoelectron has to transition to an unoccupied level. There's no real requirement for that to be a level in the continuum as opposed to an atomic level. It turns out that that it just has to go, so let's just say K level, it has to go to an empty P state. So if the atom has empty P states that belong to the atom, then that can be occupied, or that can be one of the transitions. Generally, for bare atoms, and for most systems, even for like insulators, there aren't very many P states available. There are a few select P states available that are bound, not in the continuum. So once you get above the threshold, you're in the continuum. You're 10 volts above the edge. 10 volts above the edge is there's not any unoccupied bound states that that are still part of the atom. Or there are continuum levels that swamp those bound states. But right at the threshold, or below the main threshold, there are these unoccupied states. So these pre-edge peaks, or these peaks on the edge, are often interpretable as the first unoccupied states, and it's easy to think of them as atomic levels. I mean, you could also say that's where the Fermi level is. So if you make a distinction between those, in the XAS community, we're often a little cavalier about saying where the Fermi level is. It's the first unoccupied level, but it might belong to the atom or belong to the hybridized levels of the atom with its neighbors. So in the chromium 6+, there aren't any P levels of chromium, but when you have an oxygen nearby, those can hybridize with the P levels of the oxygen can hybridize with the D levels of the chromium, so giving P-like levels at the chromium atom. And those are atomic-like. And the density states is very sharp and empty, so they're a strong absorption there. I hope that is the question. No, that's right.
Cool as well.
Answer the wrong question.
I hope that was the question as well.
That's a common question. That's a common question.
Exactly.
Yeah.
And there is one more comment, I guess. The question is, does lower Fourier transform peak mean less coordination number? And such example is like molybdenum oxyanions, especially when the distortion happens. So
yeah, so in that Fourier transform, the intensity, the amplitude of that peak has all of those factors: the F, the scattering factor, and then the coordination number and the sigma squared in it. So it's not simply the coordination number in it, because if the disorder is big enough, then you can have that where you think you have one atom with a single sigma squared. You might actually have distances that are a little bit apart, but the spread between them has a lot of overlap. And so it appears to be one shell, but they're far enough apart that it really severely attenuates that peak. So it's difficult to use the intensity of that peak as coordination number because it involves all these other factors. I hope that answers that question. I hope that was a question. Okay, so I'm going to show you the Larch XAS viewer. So Larch is, as Roman sort of indicated, so I've been writing XAS analysis programs for an embarrassingly long time. I'm still working on it. I'll get it right sometime, eventually, maybe. So this is sort of the latest version, and as hinted at, Athena and Artemis have been awesome tools and well used for 15 years or so, but they've become hard to maintain. And so one of the goals for this is to not only provide better tools and to provide access in Python, but actually in Python, but to also start to be able to replace some of that functionality for some users. You can still use Athena and Artemis. In fact, what I'll show you here is that this is definitely, and you will see, this is definitely modeled on Athena with some differences, but a lot of overlap. So when you download Larch, install it, it installs the Python environment, and you should get on your desktop of Windows, Mac, or Linux a folder called Larch, and in that folder there will be some icons to launch these. So this was XAS Viewer. There are other applications. I think I might do some command line work, but most of what I'm going to show you is just through this program. So this works a lot like Athena. We're going to open some data files. So the first one in my list of open data, yes. Okay, so actually this is also in the, if you download all the materials, there's a folder CLS 2020 XAFs, and in there there's a, there actually in that folder, if you download that or go find that link, there are Larch installers. There's Zane's data, which I'll start with, and then there's XAS analysis tools too. I'm running this on a Mac. It was the only machine I had that ran WebEx well, so I'm running this on a Mac. But really, this does work on Windows and Linux as well. So I'm just going to start that over again. Actually, so I should say it works on a Mac, which is one thing that was very challenging for Athena. So I'll open some data. This file is the one I want to start with. When you open some data, it first brings up a browser to import data as new data. This file, I'm going to just look at the text of the file, is a simple file with just energy and I0 and I transmission. This was taken about 20 years ago. So here we're going to build mu, and there's arrays to select from, and we just take minus log of I transmission over I0. So that's the data we want to look at. That's the iron oxide So I'll just say, so there are other things you can select here. You can give it a group, and you can give it what the file name is described at. You can go in and edit the arrays. This one only has 3, but you can edit these. And as I'll show you later, you can also do a little bit of work, a little bit of mathematical work, say to sum some of the, to add some of the columns together. But for now, I'll just import this. That brings that in. And as with Athena, there's a list here that's the list of files we've brought in, and then we can plot the current group. So I'll refer to these as groups or data files. And here's that plot. The plotting is a little better than it was in Athena. I'm just going to say that. In that you can zoom in and zoom out. You can zoom out all the way. I'll show you some other things you can do with this as we go. For now, this is the first step is to do the data reduction. We've made mu, raw mu, but now we want to do show how the normalization is done. So there's the raw mu. So here, there's current group. There's a number of things that you can plot. There's the raw mu, the normalized mu, the result of doing the pre and post edge back subtraction, which are then here. Here is how we've done that normalization. So let's talk about that. First, there's it knows the element and it guesses E0. You can show that or not. Actually, that's what's shown here is the E0. That's the maximum of the first derivative. In the pre-edge, we're going to fit a line between this range. So if I zoom out there, a line has been fit over this range of the spectrum. Actually, one of the features of the plot is that you can click on the label to turn that plot on or off. So there's the line, and that's what it's matching between minus 200 and minus 70 volts relative to the edge. You can also select whether there's a Victorine, which is a 1 to that power level. That looks fine. We'll leave that as it is. But then for the normalization, right now we have a polynomial that we fit between 150 and 960 electron volts above the edge. And right now that's quadratic. We could make that linear, which should update that. That's a linear fit. That's not quite as good. So you can also make it a constant, which for some Zane's data is actually a fine thing to do when the data range is not very big. You can make it quadratic or cubic. And so that gives you this normalization where it goes from about 0 to about 1. There is another popular, and actually, let's see, not just popular, but good normalization method. This is modeled on the MBAC code of Tu-Shin Wang and Jim Pennerhan's student. Here, I'll plot that MBAC, mu0 with the MBAC. So that takes the modeled, is that going to work? Yeah, that takes not polynomials, but the tabulated value of E that are known, atomic only, but tabulated, and tries to adjust the normalization so that it matches the tabulated dependence. That's the known 1 over E cubed dependence. And that can actually be quite good, not simply because it's right, but because it's consistent. So if you're comparing lots of different data sets, that is a very consistent way, whereas fitting a different polynomial each spectra can give you subtle differences in between the spectra. So if you're doing comparisons of spectra, the MBAC method is often slightly more consistent. We can compare them. We can do the MBAC versus the polynomial normalization method. And for this group, right now, there is a significant difference. You can often make that quite small. I won't worry about that too much. We can also plot the normalized mu together with the derivative. You can zoom in on that, and you can see where the maximum of the first derivative is. And so that's why it picked E0 there. Okay, so that's the normalization part. I'm gonna keep going on some of this, but I'm going to stop more often through this. So I'll stop in about 5 minutes to ask for questions about this. For normalization or extended XS. I'm going to read in some other data sets. So just just to have more data open, I'm gonna read in two completely unrelated spectra. Copper metal. Again, now just like this is also like this. I have to be careful about how you read this. You might have to look at the data file. What are the columns and so on? That looks right. I'm just going to read that in, and then I'm going to read in some zinc oxide data. And while I'm doing that, I'll try to remember some zinc selenide data. I will read in zinc selenide data here. And here that didn't come up as anything because I have to go find those columns again. So minus log of I1 over I0, yes, that's correct. Again, like you could look at the file and see what, in fact, this one is old enough that it's got some crazy column names. It was able to parse it reasonably well. I will, so as I'm mentioning this, so here we have several spectra. All of them actually have a decent normalization, and we could select them all and plot them together. You could plot the selected groups. So those are all the ones that are checked here. It'll plot normalized. Of course, they're all different edges, so they all look like, they're very far apart. It's not very useful. But I will also say that you can, for all of these columns here, you can copy from the current. So all of these things for normalization, you could copy from the current to all of the other selected. So copy to selected will copy all of those parameters from the current spectra to all of the selected spectra, the current to selected. In addition, as with Athena, or to be compatible with it, you can save this as an Athena project file that will actually read into Athena. And you can also open the Athena project file. So here, and I'll come back to this. I'm going to read in one that's just for something totally different. I'm just going to read in a project file here. You can select which of the spectra you want from that project file. I can select them all and import the selected. This is of transmission copper, one and some HRFT data that we took. So in here, I could do select none and things like with the shift key, select all below, select all of those and plot those. They're kind of normalized, and now you can see those plotted together. So that's just sort of how the program works for visualizing data. But let me now, let's see, what is the next thing on my list? I'm going to skip over that. I'm going to go to the extended XAS because I believe there were lots of questions about this. So in fact, I'm going to take those proper data and just remove the selected groups. So I'm just going to remove all that data and it goes away. Oh, before I do that, I'm going to show you something Roman mentioned, and this is an important aspect for why this program was written, is that in addition to all of the processing we did, there is a buffer. It's called the Larch buffer in a GUI. Here we can actually see those different data sets. We can browse through them. We really have the data in this buffer, and then all of the commands, everything that was done so far, including reading the files and all the and some of the plotting and all of the data processing, was actually done in this command buffer. It's read. There's doing the pre-edit, and there was some auto back was done up here. Oh, not yet. Pre-edit subtraction was done for the normalization, and so you can save that, and and all of those commands can be run either from the Larch buffer or from Python. So you can play with data processing with the GUI for one or two data sets, and then use that to help with a script to then read and process hundreds or thousands of data sets. That's going to continue for all of these other panels. So that was the normal, and just getting the data normalized. Let's now switch to the XAS panel. And here we're going to plot the FEO data, and we'll plot chi of k. And that's our first pass at background subtraction. It's, for those of you who are expert in this, that's not spectacular. It's not great, but we'll fix it up. And for those of you who this is new to, let's start talking about what that just did. So I'm going to plot not chi of k, but mu and mu zero. So again, as I showed in the talk, the goal is to find this background curve, mu zero, that matches the low frequency components of the spectrum. Zoom out on that. So we have an E0 and we have a RBKG. I'll show you in a second window what the resulting chi-of-k looks like. Up here, and see if I can stack those so they fit nicely to a single window. That works. I hope you can all see that well enough. And is that if a few that affect the background subtraction, the most important of them, by far important, is this value RBKG. Basically, we're saying here, take all the frequency components below 1 angstrom and consider them to be background. If I make that very small, let's say 0.2, then the background function is very stiff, very well, and you can see the background subtraction looks still has some low frequency oscillations to it. If I make then 1, in fact, I'll increase that to 1.2. It does a better job, and maybe that's better, and maybe it's worse. Another key factor, you can sort of see this both in the data here at chi-of-k and in the mu0, if I zoom in on the end, is that the endpoints of this aren't very well constrained. So that can be, you can change that with the k weighting of the in the background subtraction. There's a k weighting. It's different than the normal Fourier transform. 1 really works pretty well, and that's an important parameter that can affect the background subtraction. Actually, E0 can also affect it. I won't go into much detail of that. Well, I guess I could try, if I just make that like 1/6, so I'll make it further down the edge. Now, I like that, put a big spike there, and that also, so it started way down here, far from the maximum of the first root. And what I find, both from my experience, is that Ceph and data analysis in general prefers the E0 to be further up the edge than you might think. So this maximum of the first derivative and value up here around 7123 is probably about right. So the way this, so that's another important parameter, and for some spectrums, it's necessarily worthwhile to play around with that value. But you don't have to play around with it too much, and you'll find a set of values that work well. You can also add clamps that don't really work very well to the high energy and low energy range to add more weight to like try to get the background function to really match the spectrum mu of E at low and high energies. You can play around with those. I find that they are available and sometimes they're necessary, but for most data, they're not actually that important. I find I could be looking at only easy spectra. So I should say though, so we have this chi-of-k, and we're going to do a Fourier transform. So let me say a little bit about Fourier transforms, and then I'll come back to a little bit more about background subtraction. So I'm not done with background subtraction, but first, the Fourier transform. So here we're going to take, I'm going to show the window function that we're going to use. That's a Kaiser-Bessel window. Just a number of available selected list here, Hanning window, and those go from, those probably the easiest to describe, especially if I make this really small. I'll make this 1. Here, from about 2.5 came in to a max of, let's just make that a nice round number, of 14.75. That's where the window function is a half, and then a half again, and then there's a window sill, or the foot of the window, the apodization of the window is 1 inverse angstrom wide. You can make that bigger. It's often worthwhile making that bigger than 1. And so as I change that, now in the top window, I'm going to plot chi of R. And as you see, that will, as I change the functions, the Fourier transform of that will change a bit. In fact, it'll change quite a bit. I can make that, say, 5, and it'll smooth it out. The different window functions really are about trying to manage the ripple in a Fourier transform that happens because we have a finite range and a noisy signal. So in fact, if I make that 0, if I don't include the window function at all, just a sharp function, you can see there's all this ripple here. That's not real structure. Well, it is actually real. It is actually real. It's just not very useful to look at as structure. And it can greatly depend on if I tweak the values of K around, those can vary quite a bit. Actually, if you're paying attention, you can see that as I go through a 0, that will get of chi of K, that will be smoother because there is an extra weight at low R and the ripple is lower. In the event, I'm going to put that back to 2.5 and then switch to a Hanning window and a value of 4. So for the Fourier transform, these values can make a difference, and so can the K weight. So the K weight could be 0. That's not very helpful. Actually, so I plot the K weight of 0. That's that function. That's not very. You can still see this distinction between the iron oxygen and the iron shell. If I increase the K weight to be K to the first power in the plot, and then K to the first power in Fourier transform, that's not so bad either. That's probably reasonable too. Looks okay. I think we can do better on the on the background subtraction than that. And then that's 2, and then we'll go to 3. And what we're really looking for here is that these oscillations are about equal size and not too noisy. So if I get a K weight of 4, the data is we're amplifying this noise at a higher K, and also this inability of the current background subtraction to really take into account the high K data. So my general recommendation is to use a K weight of 2 or 3. I think that's also about the most common in the literature. You can accidentally go up to a K weight of 5 if you want. I don't think I've ever seen anyone publish results with a K weight of 5. So if you're not using 2 or 3, you may have to justify that to yourself or to your advisor or your I would say stick with those and stick with those kind of values and you'll be fine. And now as I change this background function, in fact, I'll go back to setting this background function to 0.01, and you can see actually that what happened is that there's all of this structure actually it looks pretty good, doesn't it? But it looks pretty good except for the structure low R. And that's that there's a low frequency component to this XAS oscillation. If I increase that, I'll just step through this in 0.1 angstrom intervals. And you can see that it's moving around. It might be getting better. It's hard to really handle it. But now, once you get to about 0.8 or so, you're doing okay. There is some sort of stuff in here that you may not love, but actually that's in the data, and it's as involved with the K max range. I would say that actually looks pretty good. So all of that stuff at low R in here and the changes in that's just how you do the Fourier transform, and not such a big deal. The thing you want to avoid is making this too big, because if I make this 1.5, that will start to cut down the intensity of the first shell. And if I make it 2, it will really cut down the intensity of the first shell. It might even make it go away. And then there's the XAS oscillations. We remove the iron oxygen contribution and have only left the iron shell. And I could make that even bigger. Just for fun, I'll make it 4. And now we've removed all of the components or most of the components of the Fourier transform of the spectrum up to 4 angstroms. This actually, as you can see, this goes to 0.3 intensity in whatever units these are. And if I go back to the value of 1, that 0.3 was down. So we preserved those peaks, but we removed all of these peaks that are actually the data that we're going to analyze. So that's the real danger that you want to avoid. And how you select RBKG is to select a value that doesn't remove the extended XAS. See, I think that's a good place to stop for questions, because then I'm going to switch to a little bit more Zane's data processing before a longer break. This is a good time to go over whatever I forgot to mention, or for whatever I forgot to cover for Fourier transforms, background subtractions, reading data, processing. Let's take a time for questions, or maybe a mini break for.
There are a few questions. If you
Yeah.
then
Yep.
can go for a mini break afterwards.
No. The mini break is for the questions. That's what I meant.
Oh, I see. Okay, sounds good.
Yeah.
Okay, so there are a few questions. I will start the question about the software. So the first one is, when you normalize, how do you choose your polynomial? So why did you choose quadratic instead of cubic? And then these kind of questions, like.
Yeah, that's actually what I did. What I do is there's an option for auto where it will
Okay.
Right. So the goal is to get this to look like it's sort of matching and not doing a crazy extrapolation. I don't think that any of these data sets here go crazy enough. Maybe this one could go crazy enough. This one might go crazy enough. If I made that range shorter, so let's just pretend that I had a lot less data. Actually, 400 angstroms, 100 EV above an edge is not outrageous. But if I make that, then you'll see here that this cubic extrapolation there of just that data range can make a normalization that's just obviously not going to 1. It's at least 10%. And if you're doing Zane's analysis or any linear analysis, or want the coordination number to better than 10%, then the normalization is definitely important to get as good as you can. I would say you can generally get it to about 5%. This one is clearly off. But if I just make that linear for that, it's already much better. Go back and look at that edge. Linear for a shorter range. So as the range gets shorter, you want to have less power in your polynomial. The get-back method seems to work reasonably well for all for very very short data ranges. The M-back method can be quite good. If I show that, there we go. Because that's just 100 volts by the edge, but it's doing an okay job. There's an energy shift because the tabulated values are shifted to the bare, not the. So they don't have an energy shift. They don't have a Zane shift, but that does an okay job actually for that. So if we compare linear and the polynomial, actually those are like right on top of each other. I have to really zoom in to see that they're different. So those two methods are both quite good. So I guess for recommendation, I would say use auto or use selection of the polynomial, or use M-back for the shortest data ranges.
The next is how to remove glitch here.
Oh yes. Right. That's
glitching
okay,
the exhaust setting. Yes.
Yes. That's my next. Awesome. That's next. Actually, you can see in this iron oxide data way out here. There's a little thing. Oh, wrong data set. But let me go to iron oxide. This data is not very glitchy, but you can see a thing here. I think that's the one that gives that. So okay. So let me see that. Actually, so here in XAS Viewer, there are 2 menu items, or 3 menu items. On Mac, the menu bar is up at the top. On Windows and Mac, or Windows and Linux, these will be like up here on the piece. There's a file menu for opening and saving data, and getting to the Larch history buffer. You can do actions on groups, so you can select and merge groups, which I'll show you in more detail in a bit when I read in more data. For deglitching, there's under data, there's deglitch data. This brings up a small window and I'll zoom in on like this point, and I'll just say, in fact, let me do a thing here. In the plot window, I'm going to configure this, bring up this plot. You can change the colors and this so on. I'm going to use the symbols, just make sure that the symbols are shown in that. And then I'm going to, just using the arrow keys, I'm moving around to panning. So I'm going to the end of the data range. And let's just say that I want to, actually, it looks pretty smooth, doesn't it? But let's just say that I want to remove a point. So I'll just click on the point, and then this pin icon will grab that value, and I can remove the point. And now there's original and current, and I remove something above 8,000. And if you look, that's the current data, or the original data and the current data. And I could save that. I could save and overwrite here, or I could save it as a new group. So just call it with the default name of clean. You can name it anything you want here, but I'll just name that as clean. And now we have a new group in this list that has that point removed. You can also say you want a whole band of a range of energy. So if I just say 8050, or go over here, 8050 is too high. Yeah, 8050. Or if I just click on that and pick this number, then remove that range, then that will take everything above that energy range. So if you hit another edge, you can just remove all that. And then you can also put below or between. Actually, so if there's a section between where you have some Bragg glitch, you can remove 10 points in a row, or below. And for some of us, often the first data point or the first few data points are questionable. You can just remove those, and they often screw up. So you can say, click here, take that, and remove everything below that. Okay, so that's deglitching, or removing some points or modifying the points. Again, you can overwrite that group or save it to a new group. There are other data processing windows, pop-up windows that come here. You can recalculate the energy, so you can do an energy shift. You can also like auto align to a different spectra. It doesn't really make sense to auto align iron to copper. So I'll read, but you can do an energy shift to 2 volts and change that. So on. Let's see what else is here. You can smooth the data, and you can bin. So if you have data that's collected at some beamlines that do fast spectroscopies, you may want to rebin the data. And this dialog box can help you do that, to put it onto what I'm going to call a typical or a normal or maybe a reasonable XAS grid that's sort of shaped like this. And you can then save that. So this would interpolate the data onto this grid that goes from pre-edge range, a Zane's range at 0.25 eV range, steps, and then you can save that as a new group as well, even if it's oversampled quick XF data from some beamlines that save thousands of points. There's also, actually, let me read in some other data to better show this. In fact, how do I get rid of all of these? This is like going on to the next part of the demo. So if there are questions you have, you could just keep asking them, or because
I'll just read the next question. It's pretty specific.
Okay.
There's a measured spectrum on arsenate, on distorted arsenate, and it's supposed to be distorted structure and high Debye-Waller factor, and the height of the peak is supposed to be lower than on references. Why could this be that the height of the peak is as high as on an undistorted material? Or I can generalize this. Sometimes we see that the amplitude of the XAS oscillations, for instance, from the fluorescence measurements is higher than for the transmission ones. Or the amplitude of the XAS on the distorted material is as high as on reference. There's no damping connected to the Debye-Waller factor is visible. Why could this be? What could it?
I guess I would want to look at the details of that. Generally, so okay, so there are a couple of different things that could be happening. transmission XAS data is remarkably challenging to get excellent data on, unless you have a very uniform sample. And so if it's a liquid, it works, and if it's a metal foil, it works. And if it's a high quality nanoparticle system that is smooth, it can work well. But for anything else, for powder samples where the grain size is tens or 50 microns, and you're trying to make a uniform sample that's 10 microns thick, it's actually pretty challenging. So there can be effects, often called pinhole or reduced absorption effects, that actually affect the transmission XFs as well as as much as the fluorescence XFs. So in fact, the data I have up here, I was just starting to read in data that's fluorescence XFs, and it's a little suppressed due to overabsorption. And we'll get to, and I was going to show partly how to work with that. But for transmission XFs, there are distortions that can happen too. But I'm not sure that that's really what's happening if the XF oscillations for fluorescence data are higher than for transmission data. It could also be that the normalization isn't done quite perfectly. That's usually a 5 or 10% effect, not a huge effect. So I'm not sure. I guess I would want to know more details of what the materials and what the spectra are.
Sure. Yeah, I mean, it's a very specific one. So maybe the question was asked if there are some general factors that influence it. So I think we Then another question is how to input a reference channel and calibrate the energy as a reference.
Yeah, right. Yes, I did mention. So for this, right. So I read in some fluorescence data. I'm going to read in a bunch more. So I'm going to read in a series of fluorescence data that I'm going to use for. I want to measure bring in all of that iron. This is all a series of iron fluorescence. This is all iron oxides, actually iron in glass in basaltic glasses or related glasses. They'll all be oxidized to some extent. Okay, so right, for reference, you have to read in the separate channel here, and then the energies. So if I say, so you can read in a file twice, once with the data and once with your reference channel. That's probably because I find that while many people are using reference channels, they're often hard to predict where that reference channel is. So I guess I should take another step back. For what this program can read in right now, it's pretty reading in most text files. I have samples from lots of beamlines, but it can't read in everything. And in fact, especially in this day and age of like using Python and fast detectors, you might want to read in data from other sources, like say HDF5 files that get streamed by your data set, or a MongoDB database or a Postgres database or something. You may want to get data from some other than actually a ASCII text data file. So Python can do that, and these tools can be used to do that. But this program right now reads text files, and I've been contacted by several people over the last, say, 6 months or a year even, about trying to get a standard reader for HDF5. And I think that's doable, but right now that's not working. Anyway, so that was going to come back to, so that's all also to say that like the reference channel, I don't know if a good way to encapsulate this is always a reference channel. So for here, you have to read it, you just read it in twice, once with the reference channel, once with the other, and then you can say from data, recalibrate energy, and you could align to say spectra. And actually those are close. There's a so apply the shift, and then once you have a shift that you like, the foils from two different sets, you could apply that shift here to all of the selected groups, and then you could make you could shift all of those groups. Is that clear? I think that's, so there's a 0.2 EV, 2.5 EV shift between those two, or there will be to auto-align those. So then you can take a set and apply an energy shift to any of them. So I hope that was a sufficient answer. For here, so this is a pile of Zane's, or a good representation of Zane's data. It's definitely not 1,000 spectra, but if you put all those together, you'll see that there's a good set of consistent values, but quite a bit of variation between them. In fact, I think if I get this right, there's sort of two main sets of data and then some in between. So there's clearly some, for those of you who know, some iron 2+ and iron 3+, and then some states that are sort of mixed in between. This one in particular. And for this data set, what I was going to show you is among other things, analyzing these pre-edge peaks. And I'll get to that, but there was a question, the reason I brought these in first was because there was a question about corrections. And so I'm going to over-absorption corrections, or sometimes called self-absorption corrections in the oldest literature, can also be applied. So if you know that your sample is over-absorbed, so what happens for over-absorption, which I didn't cover yet, is that the atom of interest, so for fluorescence data to work, the assumption is that the atom of interest is a low concentration. And if it's at 5 weight % or higher, you can get that enough of the absorption happens by the element of interest that the fluorescence intensity is not simply mu, it's not proportional to mu. It's there's a distortion because a significant fraction of the absorption happens by that element. In fact, if you have a pure compound, so if you have a metal or a iron oxide, and you measure it in fluorescence, the spectra, the Zane's and XAS spectra would be greatly attenuated. So if I just say here that I know this formula for this spectra was iron 0.05 MgSiO4 approximately, then this is the correction that would happen. This correction to happen. Why isn't it happening? This should be working. What did I do wrong?
I think you are missing 1 0 in iron, but in the form, no. That's good.
It should be okay. Actually, it's usually good at I think I have, I don't know, let me just try this. So that works. No, it's something else. I don't know. What did I do wrong? The demo is always going to fail, right? The demo is always going to fail at one place. Really, this works. FE 0.5. Actually, so for those who know, this uses the flow Zane's approach. There we go. I don't know what it was. Not the Pfeiffer approaches or Booth, Corbin or Pfeiffer approach that are better for extended XAS. This is mostly designed for Zane's. Like those other approaches can be implemented easily, rather easily to extended XAS data. This is mostly about Zane's processing. So there's the correct data, and if we increase that iron concentration, so if the iron concentration was like 2, then that correction would get even bigger. Actually, it gets even bigger, and the pre-edge peak gets suppressed. The whole spectrum gets increased. So you can go crazy on this if you were to say that's like 22 and go bananas. Maybe this data is clean enough that it actually works okay to say it's really overabsorbed. That's probably way too much. So knowing the stoichiometries of the actual sample is important. People often use transmission data on the same sample, which might be noisier, but won't have this effect. It might have different effects. Won't have this effect. And so to try to match those. Or you can say that you know the stoichiometry. Actually, when people know the stoichiometry, it's often the case that you have to tweak that a little bit to get good overabsorption corrections. So focus point 2, do the correction. It's not a very big effect. So the overabsorption correction can be can be significant. It's not always huge, but it can be important if you're doing Zane's analysis to make sure that those are done consistently for a set of data. And then again, you can either overwrite that group or you can save it as a new group, giving it a name with a default value, with a default name, absorption corrected. I'll just remove that one from the list. We don't need it. Okay, so I think, so again, like if there are questions, you can just keep asking them at this point, because now I'm going to go into a few of the Zane's analysis.
So there's another question. Basically, it's more about, can you explain a bit about the RBKG? Is it representing the phase correction, or a bit explanation could be helpful for people?
Yeah, okay. Let me go back to that. I'll read in the iron oxide. I'm going to read that incorrectly. I should also say, like, I'm reading these files in one at a time, but again, this reads in Athena project files, so that's typically what I really do, is to save the data. Okay, so let me go back to the plot this. Okay, RBKG is the parameter used to select when we select the spline. We're going to select the spline. Plot. let me weirdly plot chi of R with the view, but not showing chi of K at all. So we're going to select the spline, the BKG argument. I'm going to go turn the little symbols off of that, so it'll be a little easier to see. We're going to select the spline so that the Fourier transform is minimized below RBKG here equal to 1. If I set it to 0.5, well, the process is selecting that spline so that the values of chi below half an angstrom are minimized as small as possible. And if I make that, so that's the meaning of that value. If I make that 3.5, it'll try to find the spline so that the values of this part of the spectrum, chi, below 3.5 angstroms, are as small as possible. If I make that 1.5, it'll find a spline so that the values below 1.5 are as small as possible. It's doing it for a transform, so there's also a k weight and a k range to go into place. For the k range, we basically take the whole data range, but you can the k has an effect too, especially because it can affect this higher energy portion up here. With a lower k weight, it's not paying much attention to those high k values. With a higher k weight, it's paying more attention to those high k values. So actually, it's like k weight of 2. You saw that you can see that the spline at the threshold at k equals 0 goes a little bit nuts. Make that 1, it's sort of in between. So a value of 1 or 2 is usually about right. And then, of course, it's taking chi of k, so where the energy threshold is defined also matters. So the RBKG is the parameter, and it's just picking which Fourier components to remove from the spectrum. Is that? I hope that's good.
I hope as well. I guess it was good. There is one more question. It's not. Yeah. It's about the compatibility of the softwares. Like, can they have Larch and Demeter at the same time installed on the same computer?
Yes.
Because basically, what's the question in detail is that once Larch is installed on the PC, Demeter automatically replaces the IFFF library and uses Larch. Is that correct?
So I think that depends. Can use Larch as its backend, but it doesn't have to. I fully recommend that it does. there are mistakes. There are things that have been fixed.
Okay.
And definitely from a how many spectra can it handle point of view. There are problems with using the iFablet library. So it's okay to have them both installed. Yes.
The next part of the question is, I think you covered it, but is how to use the meteor with iFablet and separately launch in the same computer.
Yeah. So I can't. So in Demeter, you can tell it to use Larch as the backend, and in some cases, we'll be able to find it and use it automatically. But actually, I can't run Athena on the laptop that I'm showing that I can run. I don't have a laptop that I can run both WebEx and Athena on at the moment, possibly ever. So I can't show you that, but it can be done. There's a setting in Demeter which backend to use. So that can be.
Fair enough. And there is one more that they want to know what is the limit with data matrix of the Larch? What is the limit with data matrix that can be managed by Larch? Because for Athena, it was a bit about 40, I believe, if I'm not wrong. But is there any limit?
Yeah, I don't know what the limit is. So I will say that. So basically, thousands of spectra can be handled. We often have projects that are 50 to 100 spectra without any problem at all. There aren't any explicit memory limitations. The Python that's used is single-threaded, so it can get slightly slower than you would like for a modern multi-core machine. So multi-processing or being able to use multiple cores is not very easy to do with most versions of Python. So single-threaded, but those single threads have no memory limits. You can easily handle gigabytes of data. Larch itself is just a Python library, so we can handle 8 gigabytes of data. We use it for. I'm showing you the X-ray absorption stuff. We use it for X-ray fluorescence mapping, where the data sets are hundreds of gigabytes, and it's using HDF5 and reading maps, and that's no problem. So effectively, no limit. Practically, maybe the GUIs handling thousands would start to cause challenges. I think that any GUI handling thousands of data sets would cause challenges from a user interface point of view, not so much a data management point of view. So, but if you're writing scripts, you can just gigabytes of data per minute. So. Okay, so we have time to do some pre-edge peak fitting and some linear combination analysis, which is good. I'm going to just remove this data set just so that okay, so we have this set of data for, and I'm just going to go back into the Zanes world for iron oxides. So there's sort of two ways there are at least two amongst the ways to analyze data. One way is to analyze those pre-edge peaks. So if I plot just one data set here, is this the one I want? Yeah, let's try this one. So you saw that there was a variation in these pre-edge peaks. It becomes more reduced or oxidized. One classic way to analyze Zanes data, especially iron and other transition metal oxides, is to do a pre-edge peak fitting. Let's fit those peaks to known line shapes and get their intensities or like the centroid of that, and because that can directly scale to oxidation state. So for this, there's sort of a specialized Zanes pre-edge peak fitting tab in the Larch XAS viewer. It starts with fitting a base that's always not very good. So the hard part is getting the baseline kind of defined, because what this wants to do, we want to fit the spectra between the two gray bars over this red curve. We want to fit the full spectrum of that. We know that there's like some background piece here, and then there's these two peaks. So I'm going to say, as a baseline, I'm going to model that as a line, a linear component. Actually, you could probably model it as a constant, but I'll leave it as a line. Then a peak, it's actually a Lorentzian that's peaked up over here. So if you imagine there's a Lorentzian that goes like this over here. And now you could say that's the 4p level. So now I want to fit that background, but I don't want to fit the pre-edge peak. So I want to say I want to do a fit between this energy range, and I might increase that so I'm fitting more like here. And actually what I'm doing there is I'm clicking on the plot and then clicking on the little pin icon. So that makes it to grab that value. I'll make it a nice round number just so I can think about it better. And I'll go to 17, 18. And then for this, where those black dots are, I'm going to say ignore that portion of the spectrum. That's where the pre-edge peaks. Ignore that portion of the spectrum and fit that baseline. And now I have a better like start of a baseline. And like this is only to get started, so that's all okay. Actually, it reports also in this like what is that pink line? That's where the centroid is, and it says the centroid right now is 70.1 plus or minus 0.04. That's the centroid of those peaks. That's after baseline subtraction. That might be enough analysis. That might be all you really care about. What's the centroid of those two peaks after I subtract a baseline? It's a decent baseline. But we can go further because we can add models. So this is just like simple line shapes. So there's not much like physics in this, although except for the point that these transitions are sharp and so known to be give good line spectra, and then it's molecular orbital theory, using molecular orbital theory, and it's not wrong. It's just not highly theoretically complex. We're going to fit Gaussians to these peaks that we know are peaks. I selected one Gaussian one now, so here I have the components that will make up the model. There's a background peak, a background line, and a Gaussian. I'm going to pick values here. I click there, so now I click twice on this plot around that peak, and it will like draw a little Gaussian. That's good enough of a guess. Actually here, and now I have a Gaussian, it's going to have this first start for an amplitude value. I'm going to make that be positive. I'm going to say I know that peak is positive, just insist that it's positive. And then there's a center and a sigma. Actually, it also reports what the full width half max and the height of that peak will be. And then I'm going to add a second Gaussian because I can see that there's, there are two. I can see that there are two. There might be three. And you could probably spend 2 hours talking about whether there's three peaks there. And I'll do the same thing. I'll just insist that that's positive. Actually, for this peak, so this one was centered around 7113, and the previous one was 7111. I'm just going to say, let's say that this one can't be greater than 7112, and the other one can't be lower than 7112. That's just to help keep those two peaks from flipping during that would be possible to do. We'll just prevent that from happening. And now I'll go over here and I'll say fit that model. Let's hope this works. Yes, it worked. It kind of works, actually. So two things happen. So the plot shows up. Here's the plot to still we have the baseline. Actually, in the fit, the baseline does vary. So we started with that baseline, but now we're also varying those parameters. We don't have these two peaks, the Gaussian 1 and Gaussian 2. Over on this panel, we have the results page. So it's got some fit statistics, chi-square, reduced chi-square, some other information parameters, and then all of the parameters. So it also reports a centroid that it's now drawn there. That's the centroid of those two peaks, not the data, the centroid of the model peaks. And then it also has the parameters for all of that were varied in the fit. There were 11 parameters varied in the fit, 3 for each peak, 3 for the 3 for the baseline peak and 2 for the baseline line. And you get the parameters, you get the standard error reported for each of those. And then also when you click on one of those, it will show you what the correlations are with other parameters. So I think if I scroll down here and look at the baseline slope, that will be almost completely correlated with the baseline intercept. So that could have been a constant. It's okay to leave it, but that increases the uncertainty for those two a lot. But so that's the pre-edge peak, and you can save this model. So you can save that model to a text file, and then you apply that model to hundreds or thousands of other similar spectra. So you can fit all of these. There's not a fit all yet. That's on the high on the list of requests. Is just, now that I have this, I want to go fit all of those and get a report from that. You can though plot that with the residue or with the residual of the fit. Let's show that, because this is something that we see too. We often see with this data. This is data collected from my beamline at the APS, where the energy resolution, this was done with a 301 monochromator, and the energy resolution is actually pretty good for that, because with an undulator source. So you can see in this residual that there's oscillations around that. Like something is wrong with these peaks. Something's not quite right there. Either we've missed a peak or there's a third peak. One way to think about that though, so we could try adding a third peak. I'm going to say, let me just try something slightly different here. Let me delete these two Gaussians and redo the fit using void functions. So I'm going to do the same thing. A void function has the possibility of another parameter, but we don't necessarily need it. And I'm just going to click on that. That will do the same thing. And then another void function, zoom in on that, pick that. Again, this is the same thing. I'm just picking where that void function would start. And I'll do the same thing here. I'll say that the amplitude has to be positive and that the higher one can't go below 71.2. Actually, for this data set, these constraints or these bounds aren't important. I can say that one goes 71.10 and 71.12, and I'll make that positive. If you know, a void function also has other parameter, which here it's parameterized called gamma, and that's just set in this model. That'll be set to be the same as sigma. So I've constrained that to be the expression void 1 equals sigma. We could allow that to vary separately. But even if I just do that and fit that model, now I get another fit, and I'll plot that with the residual. Plot with residual. Come on. There. Those got smaller. There's still much of the misfit is now this peak, part of the peak. And here in the results page, the fit number 1 is the most recent. That's what the two void functions. That's the most recent, and the previous one has the Gaussian. So those are both recorded, and you can see that the chi-square went down a little bit, not a ton, but a little bit. And much of the misfit is actually in this portion of the peak there. So with that, you can compare different models and decide which model is the right one to apply to all of your data sets. Let's see, what else did I want to say for that? I think that's enough for pre-edge peak fitting. Actually, you can export the model as well, or get an export of the data that includes all of the components to a text file. So if you want to plot those separately, you can. You can also plot the baseline subtracted. So show me subtracting that based on those two peaks isolated, which in some literatures, this is often what's plotted. And again, this could be tweaked. I'm not saying that is the best fit to that data. That's how you start with those analyses. So I think that's done with pre-edge peak fitting. I'm going to go on to the next type of Zane's analysis, which would be to notice that in these spectra, there are a couple of things going on. And it would not be unusual to ask yourself, how many things are going on? How many different spectra are there? And that's where PCA, or principal component analysis, can really come in handy. Because you could say that each of those is separate, but maybe there's not that much difference between them. So with PCA, you can take a set of spectra that you know approximately nothing else about. You assume that they're well normalized and that they're all the same edge. And you can say how many different things are actually in that data. So if you say, select all of those and say, build a model with the selected groups, you get, I hope it's going, I'm almost sure it's going to go. We got two plots coming up here. The first is the components of that data. The main component, the first component, the most important component is the mean. That's just the average of all those spectra. That, of course, is the easiest way to think about the data is the mean. If you subtract the mean, then the main difference is this part of the spectra. Now you can already tell that these are not real absorption spectra, but they are the components that go into your data set. And so you can ask yourself how many of these are above the noise level. And here it looks like, this says there's about 4 above the noise level. There are different ways there are a number of ways of deciding that number of components. 2 of the methods are by looking at what's called a scree plot, or looking at the variance. How much of the rest of the data, you take all the data and subtract the mean. Then you find the mean of that, and you subtract all the data, subtract that from all of the data, and you continue until you've reached the noise level. So how much is the variance in the data? How big is the variance in the data as you go down? And this is plotted on a log scale. I plot that on a not log scale. I think if I go here, I can plot that on a not log scale. Now this significance, the variance, drops off sort of exponentially. So that's often called a scree plot because it looks like the side of a mountain is collapsing. Usually, and we typically plot that on a log scale. And you can see that as I plot that on a log scale, we have a component that's almost 1. That's the first component after the mean. There's a value that's just above 0.1, and then the value that's just above 0.01, and then a value that's about a part in 1,000. And that's probably the noise level. There are 4 components. This says that is significant, and then 2 that are not significant. So we could just take the first 4 components after the mean as significant. And this one here that would show up in brown is not only tiny, but like at the noise level. If I can get that to be plotted alone. That's in the noise. That's not going to be useful for modeling your data. There is, in addition, this indicator value, which should have a minimum when you've hit the least significant but significant component. So the value having a V shape and having a bottom at 4 also, like these both have good indication that there are 4 components of this. Okay, so I used all the spectra for that. So if I were to say, I'm just going to pick like a few randomly. Let me just I will pick them randomly. I'll take those 5 and do the same thing. Build a model with those fewer components. This, I think we'll still say there's about 4. It's going. Now it says there are 3 components from that. By selecting fewer components, we have now fewer spectra. We have fewer model components. But now you can ask yourself, is this other spectra, can that be described with those components, with those significant components? You can ask yourself, test this. This is sort of transform analysis. Can this group be modeled with those components? So you test that current group, and this will show you a fit of those components with that data set. So here's this data set. Actually, this data set is kind of noisy, and the total fit here is there. So that's actually a pretty good fit. I should probably have worked on the background subtraction a little better. But so I would say, although this is getting on the noisy level, chi-square is far below 1 here. So and the residual plot has no real obvious structure to it. So it seems reasonable to say that whatever components make up these 6 spectra also make up that one spectra. We haven't learned what the spectra are, but we know that there are about 3 or maybe 4 of them, not more than that. They're not completely independent spectra. And we know that this one would be able to be modeled by that same components. So then we could go to linear analysis and say, if I said this one was a combination of those 3 or 4 spectra, what would those be? But let me switch now to a different data set, because we're getting close to, I want to, that's a fine set for doing pre-edge subtraction. I want to select none and remove all. Bring in a data set that has been honed for this kind of work. This is actually from that Bruce put together, Bruce Ravel, on gold. And here I'm just going to select all and port these. In the meantime, we'll put these away. We'll come back to, we'll just try that PCA again. So here we have a number of gold spectra and a bunch of model compounds. And we could ask ourselves, so if we use all of the gold standards, let's say here, select all below, we could go do the same. Well, first let's plot them, make sure that they're all there. They're all there, and I might tweak the pre-edge subtraction. These all got set, so I'm going to select all. I'm going to do this trick, and I'm going to make this like minus 75. That's like flatter, and I'm going to copy that to all the other. And now it does a little better on this end. It's still not perfect, so I might typically want to do a little bit better job in normalizing these spectra, but I'll plow ahead in the interest of time. Actually, you can see there's a lot of variation there. So it's a fair question to ask, how many components are there? So let me just take the models here, select none above, just take the model compounds and build a PCA model with those spectra. And here we can see it likes that there are 5 different components. I mean, these are model compounds, so it's reasonable to say that those are really different. And all of them are pretty good data. There's 9 of them, and it says there are 5 different things. And actually, that's a reasonable result, because some of these are actually not very different. You can, for anyone who knows anything about chemistry, those are actually not very different spectra. And you can see that the components, even if I remove the component 1, obviously real 2 and 3, these ones down here, they're still like, that's at the noise level. So it's completely reasonable to say there are 4 good components. And now we can do the target question and say, if I say take this spectrum here, how does that model with those known components? And it can do a pretty good job. I'll remove the mean there, and that's the data and the fit of those components. So it looks like 5 or 6 components from those set of standards will model that data really well. So now with that piece of knowledge armed, we can do linear combination analysis. So we can say, use the selected groups as components, and we have a lot of these. So I'm actually going to I won't pick. Actually, if I plot, let me go back to the normalization and start plotting these. We know that 5 components are going to be enough, and you can see here that the 3 plus and 5 plus are pretty close to each other, and actually these are all pretty different. I can say, yeah, I'll just say use them all, and then we can also say, make sure the weights sum to 1, and then fit all the combinations with the maximum number of 8. I might just take one of these out just for now to make it a little faster. And then say that group, this D7 group, fit that. And this will also, this will run through all of the possible combinations of those model spectra and try to figure out which data set, which linear combination is the best of all of them. So this is a good time for questions, and I think this would be the end of this part of the lecture, and really ready for a small break. So here, in fact, so this is a good time to talk about questions. So here it says this spectrum has these components: gold foil, gold, some hydroxide, some thiocyanide, some aqueous chlorine, and a total. But then there are also that's that fit, which gave a chi-square of 0.042, and then this one, so here, not very different fit. These are all pretty good. Actually, these are all probably degenerate fits because they're all probably about the same. And then there's a fit here, plot this fit. We could also, so that's plot 9, it should plot. So that's not too bad either. The first like 3 or 4 are probably all identical, probably actually identical. We could also say here, plot the 5 best fits, and those will be also like, approximately, those are all about equally good explanations of the data. And then again, you get the different weights for the different, for each of these fits. You get a different weight value for each of the components. So that's linear combination analysis, which I think is actually fairly similar to how it's done in Athena, and maybe a few different bells and whistles. I guess that's a good time. We're at 10:30. That's a good time to stop for questions. I think I've covered everything I meant to in the first half of this workshop. So any questions about data processing or Zane's analysis would be awesome.
Hey, there are a few questions. I know that we may run into the break time, so you feel free to stop answering, and then we can start after the break.
Yep, that's all okay.
That's okay. Okay, so I'll get through the questions. The first question is, but is the test current group with model the same as doing a target transfer?
I believe so. I believe I believe that those are exactly equivalent, but it could be that some implementations of PCA do that slightly differently. But that gets into the weeds of whether you're doing like independent, like ICA or PCA or other methodologies for how to do component analyses. Yeah. But basically, yes.
Okay. There is another question, is more a general kind of question. The question is how problems on normalization or measure could affect PCA from your experience. Like by your experience, do you know how they affect?
Yeah, so normalization, correct. That can mask itself and be viewed as a component. Like if the normalization was way off and it was a half instead of 1 for one of the spectra, that would look like it was a component. So it can be very important.
The next one is basically again a general question. Any plan to expand MCR ALS analysis in future?
That's great. Yeah. So I don't know who asked that question. So, but great. If so, there's let's see. Yeah, there could be plans to do that. It's not an unreasonable thing to add. We need someone to vet it. My concern, and I think this is not only mine. The concern is that it's easy to get an answer. Actually, with all of these linear methods, and I will include PCA, linear combination analysis, the regression analysis, which I didn't talk about for lack of time, and all of the target transformation and all of the machine learning methods that will be shown later in the month or whatever, you always get an answer. And it's challenging to know that answer isn't completely wrong. And it seems like that with MCR ALS, there is always a question that it can give you hard to understand or hard to believe results. And yet it always appears to be a true, it always presents itself as being an answer. I think that's a large part of it, is vetting the quality of the results. So I played around with it, and if someone was interested in implementing that or interested in helping, or had good test data and results, I'd be happy to work with them on that. I think that getting quality assurance is the hardest part.
Okay. The next one is again your preference. Do you prefer? I don't know what I'm going to ask. Do you prefer linear combination fitting or PCA? Is there any preference in your experience?
Linear combination analysis can tell you, or at least like MCR-ALS, it will try to tell you what the components actually are. So that's a very useful piece of information. In this result, if I say this one and plot this fit, this is asserting whether or not it's right with, from a quick demonstration analysis. This says that a fair amount, like 70% of this spectra is explained by iron metal. And for that, I would actually say that's reasonable. Like that spectra has a lot of iron metal in it. You can tell from this peak right here. That's reasonable. And it tells you what the physical components actually are. What PCA is really good for telling you is not what the components are, but how many there are. And for whether spectra are consistent with one another, that is, whether the target transformation of one spectrum onto the other is in the same group. So whether those can all be modeled by the same fundamental components. But it doesn't tell you at all what those components are.
I see. And the next one is that, do we need to know the fingerprints of different components for the PCA?
That's just working on the mathematical functions of the data. So you don't need to know what any of them mean. And it doesn't tell you what they mean. It just tells you how big the differences are between the data sets. So they don't have to be necessarily interpretable differences in the spectra. I mean, if you can't interpret the differences, at least qualitatively in the spectra, point to one and say, yeah, that looks like iron metal and this one looks like iron sulfide, then you're going to have a hard time understanding the data anyway. But PCA works with any spectroscopy, any set of data. So it works on facial recognition or election data. It doesn't need to work on any aspect of chemistry. So it doesn't need any knowledge about the spectrum. Okay,
fair enough. And I'm going to take this last question and then we'll go to the break because I guess you need a break as well. The question is it's more like about how to choose the proper reference. For example, like some of them have more intense features and then some of them has less, but if you choose them all, you may lose the chi-square. So do you have a general kind of comment on how to choose a proper reference spectra for the LCF?
Yeah, I would say it's actually a good idea to use the PCA to make sure that are your data are represented by those components, or the components of those reference spectra explain your data. That's a good thing to do. And then you probably have some actual chemical intuition about the structures that actually apply. So that gets to like the sulfur versus chlorine ligand thing too. If you know that there are sulfur ligands, you want to include the gold sulfide. But if you know there aren't, you want to not include that, especially if you think there are chlorine ligands, because those spectra are close enough that they can be a little bit overlap, and so it's difficult to tell them. But if you know from other methods whether something is there or not, that can help dictate whether you include them. We went through the basics of X-ray absorption and a bunch on the Zane's analysis, a little bit about using the software in general. So we're going to continue and do the extended XAS in more detail. And we're going to go for as long as we can stand it. So we hit, in the previous talk, I've gotten to about this far in the XAS equation that there's a scattering amplitude, a 1 over r squared, and sine 2k of r plus a phase shift delta. That's for one atom. Then we add neighboring atoms, including some disorder, either thermal or static, in the distribution. And again, with a pair distribution function model that could be as simple as a single mean square statistic or a more complicated formula. We'll skip over much of that for the day. Then we have these functions f and delta that you'll recall modulate the sine functions of the important z dependence of the extended XAS and the phase shift to the data. That's what we got to so far, and we left out quite a bit. That's slightly complicated, but not very complicated. It's going to get more complicated than that. So a break is a good thing before starting in on this. So for the simple description so far, we skipped over a few things, and the most important thing that we skipped over is the inelastic losses. That is, we thought about the electron, the photoelectron, going out from the absorbing atom, but not it scattering from anything except the neighboring atom. But an electron, especially in a dense material like any material, can scatter off of the other electrons in the material. And there's sort of two different regimes that breaks down into: the so-called extrinsic, or the electron mean-free path, and the relaxation of the other atoms in the other electrons in the absorbing atom due to the presence of the core hole. So the core hole can cause relaxation within the atom, and the photoelectron can have losses outside of the atom, intrinsic to the atom and extrinsic to the absorbing atom. And in addition, we just neglected the fact that the photoelectrons can scatter not only once from the neighboring atom, but multiple times from different neighboring atoms. And so multiple scattering can be important, at least at high K and at high distance. We should include these effects, and in fact, the calculations that we'll use from PHEF do actually include these effects, and we'll look into that in more detail. For the loss terms, for sort of all of the loss terms, the easiest way to think about this is to have a photoelectron mean-free path, the extrinsic loss terms. And that is to say, we started with a wave function that was just a spherical wave function, so e to the ikr over kr, the atom just expanding out, or the wave function just expanding out from the absorbing atom. But because this photoelectron can also scatter inelastically, that is, scatter and lose energy, it may not be able to get back coherently to the absorbing atom. So the mean-free path describes that effect. It's well known in lots of other electron spectroscopies, including electron microscope measurements, that this effect happens. And so instead of using a simple spherical wave, we're going to use a damped spherical wave. We add an e to the minus r lambda, which will take into account that as the electron moves out in distance, it also has a better chance of scattering from the other electrons in the system. And this lambda term is how far it can go, how far the electron can go before scattering incoherently. And it needs to be able to return to the absorbing atom at the same energy level. It turns out that this lambda is this mean-free path is fairly universal. It's mostly independent of the atom type and of the molecular environment. So we can include the effects. You can also fold into this piece some of the intrinsic parts. That is, especially the finite lifetime of the core hole. That is the time for a fluorescence or Auger effects to occur, which are on the timescales of around femtoseconds, which is a few orders of magnitude faster than the absorption process itself. And so that can be taken into account in this photoelectron mean-free path as well. as you'll see, this photoelectron beam-free path is on the scale of 5 to 10 angstroms. At high energies, high K, it could be as far as 50 angstroms, but it's down in the 5 to 10 angstrom range for most of the K range that we are able to use with XAFs. And so that lambda and the 1 over r squared in the XAFs equation is what makes XAFs a local probe. XAFs cannot see very far out from the neighboring atom because of the mean-free path and the 1 over r squared. You can also see from this universal sort of U-shaped curve that at very low energies, that is near the Fermi level, near the threshold, in the Zanes region, lambda is pretty big. So Zanes is actually a better probe of the entire molecular unit. It can see further. You can get scattering that happens to much further out that affect the Zanes. This is one of the reasons why Zanes modeling is more complicated. You have to include paths further out. If you want to do a sum over paths at low K in the Zanes region, you have to have that path be many tens of thousands of paths. Whereas in the XAFs region, we can often get away with it being 2 or a handful. Okay, and in addition, there's the intrinsic loss term, which although we can account for the core hole lifetime, and fold that into the lambda is typically done. There is another term that because the core hole exists, is created in the absorption process, the other n-1 electrons within that atom can relax. This often gives an amplitude reduction term, and it's due to the relaxation of the other electrons with the unperturbed, the ground state. So for the most part, this is a constant. It's not quite energy independent, but it's pretty close to energy independent for most work. The calculations we do with FEF try to take this into account, and some versions of FEF, some more recent versions of FEF, can take this into account fairly well and can show that it's not perfectly independent of energy. Josh, in particular, Josh Cass has done some nice work on this. But what we do pretty much for extended XAFs analysis is treat this as a constant. Treating it constant causes pain. That is, it is completely correlated in the XAFs equation with the value n, the coordination number. It's also completely correlated with the edge step. As we've normalized the data, if we get the normalization wrong by 5%, the coordination number, or S0 squared, will also be wrong by 5%. They are 100% completely correlated. This makes the XAFs amplitude less precise and harder to get precise than the XAFs distances. Distances come by the phase. It's easy to see how modulation happens, but getting that amplitude precisely is challenging. And this is one of the complications for why that is. In addition, we see that this value is typically between 0.7 and 1. It can appear to vary with beamline a little bit, and that's partly because although we took into account in lambda some of the electron core hole lifetime effects, nothing we've done so far has actually taken into account the energy resolution that we use when we collect X-ray absorption data. When we ask for 7112 electron volt X-rays, we get some spread in that energy. The size of that spread, the energy resolution, will actually almost exactly impact either the mean free path value, or could be modeled by changing the mean free path value or changing S0 squared. And we typically just ignore those effects because there isn't much variation in real beamlines, but part of this effect is the change in resolution between beamlines. So that means that at a beamline, we typically try to measure what that value should be for a selected absorbing atom. It should be that it doesn't depend on anything except the absorbing atom. All iron should be the same, but it might be that all iron at a particular beamline is the same. Might be a better way to phrase that. Because it takes into account some, although it's theoretical, it also helps take into account some artifacts of the measurement. In addition, so multiple sum over the scattering paths or multiple scattering. Think about the XAFs, and earlier generations of XAFs practitioners tended to think about shells of atoms rather than paths for the photoelectron to take. But if you take the more general view of scattering paths instead of shells of atoms for the photoelectron, then this allows multiple scattering to be taken into account, where in addition to normal single scattering, you can also include the effect of triangular paths, and especially important, the multiple scattering paths where atoms are nearly linear, and that can be either in a straight line like this, or bouncing back and forth twice between the same set of atoms, between the absorber and the scatter, bouncing twice. That will appear at twice the near neighbor distance, as will this, but the scattering in the forward direction is actually scattering of the photoelectron in the forward direction is actually pretty probable. That has a high amplitude. And so these paths can be important if you can go out to analyze the second or the past this second shell. If for many close packed systems, that would be the third or fourth shell. And that can also be used to measure the angle between those atoms. So if it's not exactly 180 degrees, the fall off with angle is quite big. Another effect that I haven't mentioned yet is that the X-ray beam is actually, from a synchrotron, is highly polarized, usually at least 3 nines, often much more than that. So that means that, again, assuming a K shell, the photoelectron goes out like a dipole. It goes out in the horizontal direction only. It does not go vertical. In fact, the X-axis is blind. X-axis for the K edge is blind to the neighbors that are vertically placed from the absorbing atom. It sees left and right, but not top and bottom. We model X-axis assuming that it goes in all directions and is isotropic. That works for isotropic crystals or isotropic systems or samples that have no orientation dependence. But for anisotropic systems, including, like, say, surfaces or non-cubic crystals, this can be important. The X-rays see in the horizontal direction, but they don't see in the vertical direction at all, because it's cosine squared away from that. So you can, sometimes this is very important, and sometimes it doesn't matter at all. And I'm going to ignore it for the rest of this lecture and data sets, but it can be that it's very important. You could think about that being folded into the value of F, that the value of F should just be 0 if the atom is displaced vertically from the absorbing atom. So as a result, with the lambda, basically in these other terms meant to scare you, we have a slightly more complicated formula, but still we're at the point where if we know F and delta, the photoelectron scattering amplitudes and phase shift, and we know the photoelectron mean free path, which we can calculate, or FEF can calculate for us rather easily. If we know these properties, we can determine or refine out distances, coordination numbers, and information about the distribution of atoms around the absorbing atom, and get some Z dependence as well. Okay, so let's talk a little bit about XAF's analysis. Or let's talk a lot about XAF's analysis. Okay, so how do we do that? How do we get R, N, and sigma squared from our data and F and delta? Well, actually, how do we get F and delta? So first we calculate spectra, XAF spectra with FEF, starting with a candidate local structure. Often we have a good idea of what the structure could be or will be. And it doesn't need to be perfect, and then we will refine our values for near neighbor distance and coordination numbers. And then we'll compare lots of refined models and decide which ones are best. So what we're going to cover here is how do we run FEF, what are the correction factors, how do we fit data, and then much of this will quickly get into like normal, well, sort of like standard data analysis issues. sigma or chi-square and fitting statistics and so on. So the FEF calculation, but we'll start with the FEF calculation, which is going to calculate chi of k. It's going to simulate chi of k using ab initio scattering calculations for the photoelectron. It will include all scattering paths within a cluster of atoms. So we need to build up a cluster of atoms. So we need to start with a cluster of atoms, determine the scattering paths, and then we need to calculate the atomic potentials for each atom. So if you think of each atom as in a cupcake tin, then we use what's called the cupcake tin approximation, where the atomic potentials up to some uniform level, the Fermi level typically, are used, but in between the atoms, it's just a constant potential level. That is, the electron will get out of this potential as it travels to this atom, or this atom, it sees the same flat potential. That can be important in the Zane. That can be important in the Zanes region, and it's how FEF, or how earlier versions of FEF, differ from FDM&ES of Yves Joly, which we'll hear about in upcoming lectures, where this approximation can be lifted. But for extended XAFs, this is a fine approximation. We're going to be tens of volts above the edge. Those potentials are not important. But then we are going to build paths based. So if this is our central atom, our absorbing atom, we got to build paths that go from here to here, from here to here, from here to here. And we have to recognize which ones of those are degenerate. This is in the physicist terms. Degenerate is not a bad thing. It means that they're equivalent, and then we'll calculate the XAF's contribution from each of those different paths, and that will be done by moving the photoelectron out of the atom through this interstitial part between the atoms, and then scattering. So it's propagate out of the atom, scatter, propagate again, and that can be done to multiple atom steps. So you can go from this atom to this atom, up here and then back. You can do all of those. We won't worry about the details of that. The calculation does that. In fact, most of that part you don't have to worry about at all. I'm just telling you what it does, not what you have to worry about. So from a practical point of view, the most important things are to start with the crystal structure close to what you think your structure is. This is a refinement process, this XAFS analysis. So the crystal structure is often close, but it doesn't have to be perfect. We will refine the distances that come out. So running FEF for a crystal structure will generate a series of files, FEF 0001002.dat, which will encapsulate the scattering factors for each of the paths in your structure. And then we'll use those paths as the model to build up our XAFs in the sum of paths. And all of the programs, Artemis, 6-pack, Larch, make this easier. They run a managed FEF for you. I will show you some of that, how to do some of that by hand, because it's sort of better, I think. Well, in my humble opinion, it's sometimes better to watch it happen than to just rely on magic. Although magic is good too. One thing is that you run FEF on a single structure. You can run it multiple times, and it's okay to mix paths from different calculations. Sometimes you want to be careful about that, but generally it's fine to mix them. So the version of FEF that we are using comes from a pretty old program, pretty old Fortran program, where the input file really has to be called FEF.input. It also works to generate a lot of files in a single place. So it's really best if each of these runs of FEF happens in its own subdirectory. In fact, the way I'll show you, I'll just run FEF and say, I have a folder with a FEF.input file, run it in that folder. So then the FEF.input file includes a list of atomic potentials, that is, different kinds of atoms. There's always a special atom, 0, for the absorbing atom. So in our case of iron oxide, there will be an absorbing iron. there will also be a scattering iron. So iron oxide actually has 3 different atom types: an absorbing atom, an oxygen atom, and an iron scatterer, but not, which is not. So we'll say there are 3 different potentials: potential 0, 1, and 2. Those are the and the Z to consider for that. And then we just have a list of atomic coordinates, x, y, z in angstroms, and then which potential to assign to that position in space. That's all you really need. Well, there's a couple of other things you actually need too. Most of these we'll leave out, but whole of 1, or in modern version k, means the k shell. And then you can also say S0 squared. Here, we're always going to leave S0 squared to be 1 in the calculation and then refine it in the analysis. There must be exactly 1 absorbing atom. In this case, it's 0, 0, 0. That is not required. It's not necessary to have it at 0, 0. It's inconvenient, but it's not necessary. And in addition, you can edit this file and then change how the calculation is done. So if you want to say, let's change one of those oxygens to chlorine, you could add another potential and just 3, make that chlorine, and then say that that atom is chlorine, and that will include a path that's iron chlorine at that distance. You can change the distances. There are other things you can do. If you want to say, I don't want to simulate iron oxide, I want to simulate nickel in iron oxide, or maybe arsenic in iron oxide. You could generate this file, and I'll talk about that in a bit, and then say, well, the absorbing atom is not iron. It's the iron oxide structure, but the absorbing atom should be arsenic. So then just change the Z there so that the central atom is, say, arsenic. And that would calculate the arsenic K edge for arsenic substituted for iron in the iron oxide structure. Right, I think there are other things you can do. In the interest of time, I'll slow down or not dwell on. One way to create PHEF input is with an Atoms program, which came with Athena, and actually we have a website now that can do this too. So there are websites where the Web Atoms, if you Google Web Atoms, you should find it. You can look up a crystal structure and then run PHEF on it. You don't need to start with a crystal structure. It does not need to be a crystal structure. You can take data from the protein data bank and make them up. You can take density functional theory calculations. You can take MD simulations. You don't need to do that. What you need is a cluster of atoms. Crystal structure is a convenient way to start, but you do not need a crystal of atoms. Let me say that again. What you need is a cluster of atoms. You do not need a crystal structure. In fact, you can take a crystal structure and distort it, and you can still run PHEF. Okay, so when you run PHEF, you get out a set of files. PHEF 001002. Like this. You do not need to know, you do not ever need to change this. You could, you do not need to change this, but this has in it, embedded in it, the geometry for that path. Iron is the absorber, potential 0, iron, oxygen at 2.213 angstroms. And then here are the different portions of the phase shift and the magnitude of PHEF, and including lambda, the mean free path. And there's other factors too that I'll skip over in the interest of time. So the analysis programs will use this as the kernel or the model for that one path. That contains all of those factors that we need. In a real analysis, we'll be refining bond lengths and coordination numbers. So here's some practical guide, rules of thumbs. If you're refining distances and they move by more than 1/10 of an angstrom, you should look into that. It might be that you want to rerun the calculation because the overlap of the atomic potentials may start to get inaccurate if the distance is more than 1/10 of an angstrom. Usually we're talking about refinements that are a few hundredths of an angstrom. So when you hit 1/10, that's a pretty big change. Refining the energy origin. So PHEF does a calculation and it picks an energy. It has an idea of where the energy origin is on your spectra, and you pick an energy origin like in the background subtraction for the maximum of the first derivative. If these are different by more than 10 eV, it may be a problem. Actually, it might be fine. It might be that it's right, but you should be careful about that because what could happen is that if you move the energy so much that you jump a period in the XAS oscillation. So if you see an E0 of 10 volts or more, you'll start to get questions. hopefully from your reviewers or your committee members on whether that's reasonable. Within FEF, within the FEF calculations that we're using, you could set S0 squared and sigma squared. Don't do this, it's confusing. It will drive you insane. You should set S0 squared for a set of data that's based on central atom and beamline energy resolution, and then based on an experimental standard that you refine S0 squared for and not n. I can go into that in some detail, I think, in one of the examples. Okay, so to model XAS, we have this equation, we have our XAS equation, and we may refine for each of these, for each path, the parameters that are n times S0 squared, or amplitude, E0, delta R, sigma squared. Actually, there's a bunch more for, there's a bunch more. Actually, I should be clear, we're refining delta R, the change in R. The FEF calculation has a distance for that iron oxygen, and what we're varying in the fit is a change in that distance. So that just becomes a reporting the distance and what is the change in distance. So we'll start with the R EFF, the R effective, and there are other parameters we could, and in principle, any of these could be refined. You can set them or you can refine them. So let me just show you what it looks like for rock salt. Then we'll do this one as a demo. So iron oxide is just a simple octahedral rock salt structure. I hope everyone can visualize that well. And there's our Fourier transform in blue of the data. That's the kind of Fourier transforms we were seeing earlier for iron oxide data. And then red is the best fit for the first shell. So I did a calculation. I have the FEF001.dat file, and that is F and delta, and that's the best fit to the amplitude, or it's the best fit, and that's the amplitude shown. For this, I got S0, I just fixed S0 squared of 0.75. Whether that's right or not, and I get a coordination number of 4.7 minus plus or minus a half, so about 5. So maybe a little low, but not terribly low. R is 2.10, which is also a little low, not terribly low. And then an E0 and a sigma squared that are in the range of what I would call reasonable. So that's not a bad fit. The distance is a little low. Actually, I believe this data, I believe all of the iron oxide data I have actually is slightly oxidized. It's difficult to get pure reduced. And so an iron 3 has a shorter distance, so there might be a little bit of distortion. If we look at that same fit, that's the best fit. This is also the best fit to the data. I'm going to repeat that. That red curve is the best fit to the blue curve. Really, I'm not kidding. That is the best fit. That's because we fit in R space. What we really fit was here it's shown the real part. We fit the parts together. That is the real part. That's what's really fit. The amplitude is not is not actually included in the fit. Only the real and imaginary parts are included. And you can tell we ignored a lot of the data in that fit. We fit between about 1 and about 2 angstroms. That's a good fit to 1 and 2 angstroms. And that's a fit. That's a good fit up here on the K-space. That is a good fit. That is not only a good fit, that's the best fit to the portion of the spectrum between 1 and 2 angstroms. That is a good fit. I'm telling you, that is a good fit. Those curves look nothing like each other. We neglected a large portion of the experimental data in that fit, but that is the best fit. This is why we fit in R space, because it allows you to neglect portions of the data that you want to ignore. We know that we want to analyze the first shell in R space. It's not defined in K space. The fit should be done in R space. If you're fitting in K space, you're doing it wrong. There are interesting things you can do with fitting in both K and R space or in wavelet space. That's beyond the scope of this talk. If you're fitting only in K space, you're doing it wrong. So let's talk about what analysis means or what fitting means. We need a model and we need a measurement, and we want the measurement to meet the model as well as it can. So here, this is just like a normal statistic chi-square. That's different than the XAS chi. It's chi-square. And that describes how good the match is between a measurement and a model for that measurement. So here we have a set of data or a number of points to fit, a measurement, a model, some parameters that we fit, and an estimate of the noise level. And the best fit is the one with the lowest chi-square. So in this equation, we have a few terms. We have n-fit, we have measured, we have model, we have parameters, we have epsilon squared. We need to discuss each of those terms. Each of those is something to think about when modeling XAS data. So how many independent points do you have in a measurement? What is epsilon? And what are the parameters that can or should vary? And even what is the measured data? Because we're modeling chi of R. We measured intensities in ion chambers. We converted that to mu. We converted that to chi of K using background subtraction. And then we Fourier transformed that to chi of R. That is what we're going to model. That very processed data from far. So thinking about what the uncertainties in that very far from raw data are is challenging. We need to think about that. Okay, so the number of parameters that we can reliably extract is the number of independent points in the spectrum. It's about 2k r times the k range times the r range over pi. This used to be controversial. I will tell you that it's not controversial. This is right. It's simple. It's simple signal processing. In K and R space, there are there's a range, and that gives you a fixed number of finite parameters. Each measurement of mu, each measurement of the intensity in your ion chamber is, in fact, an independent measurement of the intensity in your ion chamber. But each measurement of the intensity in your ion chamber is not an independent measurement of the first neighbor distance. Those values are correlated. The right way to think about it is how many independent points do you have in a limited K and R range? And that is the right way. Whether it's +1 or +2, that doesn't matter so much. But for a typical data range, there are about 12 parameters that you can determine from XAS. That's not much, but you only have 1 or 2 shells. So when we converted the data from intensities to chi of R, we did a bunch of things, including interpolating and interpolating the data into finite bins in K space, and then finite bins in R space to do the Fourier transform, to make the Fourier transform smooth. So the number of data points we have in R is not anywhere close to the number of independent data points we have in our spectrum. So we need to include that effect to best understand the uncertainties. I'm also assuming that epsilon here is constant. I've pulled that out, and I'll get to that. Maybe I'll get to that. Maybe I'll skip that. We also have, so now with chi-square, we also have a fair number of different statistics that we can report. Reduced chi-square is a common one to use. That's where you scale chi-square by the number of degrees of freedom, number of independent points minus the number of variables. And for that, for a good fit, chi-square should be about 1. You'll never see this. Unless you have really bad data, you'll never see this. And so we often report also which is something that people doing diffraction also report, because for them, they have a similar problem that trying to report a chi-square statistic gives them horrible results, even for excellent fits. So that's a fractional misfit, not scaled to the uncertainty of the data. Okay, so chi-square, so I mentioned this a little bit. What is the measurement? Well, actually, it's the R space, so we can say which shells to ignore, and we need the real and imaginary parts of those. Plus, we could actually say that we're not going to measure just one data set. We're going to measure multiple data sets at a time, or there's a nice trick that we came up with for Artemis time that you can measure multiple K weightings. So if you're not sure whether the K weighting should be 1, 2, or 3, you can just say use them all and fit all of them together. As long as we can generate the model for that, it's fine to extend the data in that way. You can also fit in, I'm not showing it here, but you can also fit with Larch in not just R space, but in wavelet space. So with a Cauchy wavelet that maps both K and R space. And then you can pick a finite range from those two spaces. Okay, so I'll talk a little bit about fit statistics and how we do fitting. We can go back to our data and add a second shell. Here's the second shell for including the FEF0002.dat file for iron scattering. And now we have the amplitudes of the for the data in blue and their fit for the first two shells in red. And these results are actually more consistent with the known values. Actually, when you include the second shell, you get a slightly better. Still 210, and this is 31307, which is actually not that bad. And again, if there's a little bit of I think we're going to get a better value with our data. I think there's also a little bit of 3+ iron in this spectrum. You'll notice that actually the value for E0 squared, or E0, is exactly the same for these two shells. I could have varied independently for the two shells, but I just refined that or constrained those to be the same. This is a typical very good fit. Reduced chi-square is 160 or so. So the calculations for that's at least partly because the calculations for F and delta are good, but they're not perfect. Our data here is actually pretty good quality, but so that this systematic errors dominate the uncertainties in the data, and the uncertainties in the calculation are actually important to take into account. And those are difficult to take into account. We try, but they're difficult to do. So looking at that fit second time, now here's the two shell fit, and here in the red is the best fit, blue is the data. So now this best fit is more plausible as the best fit. You can see that we're still missing things, but the things we're missing are high frequency components, that is further shells, and so that kind of makes sense. And you can also see that if we plot for this model the iron oxide in blue and the iron in red, you can see a couple of different things here which are important to work out. I'll try to show this in the demo too. The iron oxygen has a longer period because it's a shorter distance. It's a lower frequency component. It also peaks up in amplitude at lower K. That's because of the F of K it peaks up at lower for iron oxygen than for iron iron. Iron has a faster oscillation because it's further out in distance, and its intensity peaks up at higher K. If we plot the magnitude of the Fourier transform, and we plot those two separate components on top of each other, in addition, you see that there is small but significant leakage between those two curves. So saying that this distance at 2 angstrom is the place where iron oxygen stops and iron starts is not a terrible approximation, but it's not perfect either. And so actually a fair amount of weight for this range between 1 and 2 angstroms is explained by iron scattering, more than it's explained, as much as it's explained by iron oxygen scattering. And so in that initial fit to just the first shell, we were a little bit off because we weren't including the higher shell. Now when we look at the real part, I think that's the real part, in addition to the magnitude, you can see that the fit is actually quite good over this range. And in fact, where the fit is bad, past 3 angstroms, it's probably because whatever's there, we're not including the effect of it leaking in from this side too. So I would actually say that the iron here still could be questionable from higher shells leaking in. I know from the structure that that's less likely to be true, and it's the biggest peak, so it's less likely that will have a significant impact. But it's not unreasonable to say that if you're going to report the values for a shell, you should at least try to accommodate and model, at least to first order, maybe not fitting, but at least model the next shell out. And you're including the effects of it leaking in to that shell. Okay, so let me talk a little bit about this question of the number of independent points and what we can vary. For complicated problems, we really need to limit the number of variables we have. Basically, if you consider each shell takes about an angstrom, and we only have 12 inverse angstroms of data, then you get about 8 independent points per angstrom. And if you have multiple shells building up, and as you go out in distance, you will, then you really run out of information that you can separate from your model. So you'll want to be able to say, you want to impose relationships between the different path parameters. E n sigma squared, R and E0. In fact, it's likely that you'll say that E0 is just the same for all paths. You don't have to. And in fact, if you did calculations and you were studying that, you may want to allow this to be different, but typically those will be the same. And in S0 squared, you probably will set S0 squared and then want to vary n. You may do it the other way, or you may want to say, I know what the coordination numbers, I know the molecular units are for this set, so I want to fix those and allow sigma squared to take up any variation in amplitude. You may also say that you know something about the distances that are related. So in these programs, in all these programs, there are ways to say that the path parameters that actually vary to control what R is for each path is written in terms of like generalized variables, and which allows a simple system of constraints. So we can allow E0 to be a single variable and have the different paths. The syntax is a little different than this, but this is the older syntax. That's okay. To use the same value. So that parameter will vary in the fit, but each of them will be varied the same. They'll be constrained to be the same value. For some cases, you'll have a mixed coordination shell. So you'll say, the question will be, I know I have oxygen lipids, how many of each do I have? But you'll also know that you have a total, that's a fractional question, not a total question. That is, you can say, I have 6 neighbors, how many of them are sulfur? And so you can say that one path will have an amplitude that goes as X, the fraction of sulfur, and the other one would be 1 minus X sulfur. So that would give you the fractional amount of sulfur in each path. There are more complicated things you can do. In fact, the literature has a few cases of some very complicated things that you can do. One thing is that you can say for a series of temperature-dependent data, or even if you refine them all together, you may want to say that sigma squareds for different temperatures are all characterized by a single temperature. That a single temperature explains the sigma squareds for a variety of paths over a different temperature range. So there's a way to do that with it gives the Einstein model for a single oscillator between atoms as the spin constant. So this use of constraints and generalized variables allows us to use some prior knowledge into the analysis and limit the number of parameters that are variable parameters that are fixed in the model. It also allows us to sort of alter the thinking about fitting the XAS as just the XAS functions, just R, N, and sigma squared, into thinking about your structure. So you could, for example, say that the question you're asking for a metal absorbed onto a species, onto a surface, is the height above the surface. And so you can alter the height. That will affect the distances to many paths, but only with one variable, although with a complicated dependence then on distance that is actually modeled. So for example, for modeling copper at 3 temperatures, you could say I have copper at multiple temperatures and I want E0 to be the same, S0 to be the same. The distance should be linear with temperature, so not 3 separate parameters, but 2 separate parameters, and sigma would be defined as a single Einstein temperature. So the 12 parameters become 5, and we can model that as one of the fits. So these things can be done, and I think that getting close to the end, and this is a good time for questions about all of the XAS fitting, and then we'll go into the demo again for some more even better information. And I think it's a good place to stop for questions, and we can go on to a demo of fitting some XAS.
Good. So I will start if no one minds. So I have a question about the multiple scattering paths. Usually, if the structure is more or less complicated, you have a lot of multiple scattering paths building up some peaks. So is there any sense to include this fitting in the model, and how to deal with the Debye-Waller factor and the other parameters in this case?
So, yes, for sure, you can model the multiple scattering. You have a lot of paths, but if they're all, I guess, so it always depends on the system, so I can always fall back on it. Well, it depends. But in many cases, let's go back to this thing, this cartoon. We went through a lot. So, if you have questions about any of this, it's crazy. Just went through. Where's the multiple scattering? Did I skip it? No, I didn't. Here we go. So for these paths, with these focused multiple scattering paths, these are really important to include. If you're going out to the fourth neighbor in copper, you have to include those. And in fact, this one should be included too. But when you get there, you know the distance. The distances are all the same, and actually the sigma squareds don't vary between them very much. So it's typical, if not correct, to use a single sigma squared for all of those. There's a lot of different paths that you have to consider, and so you want to have just a small number of parameters. I should say that typically the triangle scattering paths where one of the angles is a right angle, because the x-axis goes out as a dipole, is basically zero. So these paths have a very small amplitude. The problem is they have a small amplitude, but there's lots of them. So it's not unreasonable to just ignore them, but sometimes they can actually contribute. They typically contribute a small amount, and you could treat them as you want to include them in the model, but you could fix the sigma squared to be some value that's reasonable, and so only take them into account in a theoretical way and say, what's the impact of that on the other shells? And it could be that's a typical approach to including at least triangle multiple scattering paths, because there's too many of them to try to fully model, and the amplitudes are low, so you're not very sensitive to them. But you can try to take them into account by including a model of them and just sort of fixing. So say, let's not let those distances vary, or let those distances vary in a way that scales with the first neighbor distance, and just set the sigma squareds all to be either some value or the same parameter. I hope that helps answer that question.
Mm-hmm. Yeah, sure. And another question is since there's a lot of correlation between different factors, how accurate, in fact, is the coordination number? Because it's affected by S0, it correlates with others.
So coordination number, it's 10%. And it's, okay. It's challenging. It's not impossible. It's challenging to get better than 10% on the coordination number in sort of an absolute way comparing to FEP. So for some cases, that's not good enough. So what you do is you measure lots of different temperatures, or maybe different conditions, and the variations in coordination number can be very accurate. So if you're measuring a series of temperatures, the relative change is extremely accurate in the amplitudes. It can be extremely accurate, whereas the absolute is much less accurate. And the accuracy, or the much reduced accuracy of the absolute intensity is at least partly that normalization and overabsorption corrections or pinhole effects. All of these other experimental data processing effects that and S0 squared, which is also energy resolution of your beamline. All of those sort of conspire to make the amplitudes of mu be challenging to get right. And actually then also making the amplitude of chi to be wrong. But you can be consistent. And in fact, if you do temperature dependence, all of those things sort of fall away, more or less, and you can be quite consistent in getting a good change in coordination. I hope that also helps.
Mm-hmm. Yeah, at least you will have more experimental points that will allow you to increase the parameter. space. There's one related question: is the coordination number for the iron oxygen shell, does it take into account the SO2?
I fixed that. I just fixed that to be 0.75, I think, for that data set. Yeah, I just fixed it. And so what, typically one might take iron oxide as the standard and say, what should S0 squared be in order to get the value of 6? Right? That might be how you actually use that data. And that's a fine thing to do. In fact, you'll get a value that's around 0.75%. So I just fixed it as if I knew, and so that coordination number might have some systematic error in its reported value.
So I know sometimes for reference for a known compound, SO0 is coming from the experiment as a measure of the beamline, as a beamline characteristics. And then you just fix it, and and you use it in your further fitting.
Exactly. That's the typical and the recommended approach is to analyze the foil, or the closest metal you have, or a good oxide standard that you trust, and you can then say, I know what the coordination number is. Tell me what S0 squared is to make the coordination number right, and then say, well, for this beamline, for this set of data, maybe this run, with this set of slits or whatever. Good value for S0 squared. And I think what people find when they do that is it doesn't vary that much. It's typically, it's between 0.8 and 1. And, when you get to the point where you need the coordination number to better than 10% to answer your scientific question, then you know how to do that well.
Mm-hmm. Yeah. A couple more questions. So one is about the accumulants. When it makes sense to include them into fitting, and
right. Okay. Yeah, I left about partly just in the interest of time. This is only a 4-hour workshop, not a 4-day workshop. Okay, so for what I find is that for most metal oxides, most solids, metal oxides, you don't need the third cumulant, or you don't have enough data to say. So in the literature, I've said in the literature many times, we tried a third cumulant, it didn't make any difference. That's sort of a typical result, I think. That might be the most common result. But there are cases, especially for softer materials, so metals, and things at high temperature, where that third cumulant can be important. And that it can be important if you're really focused on what the distance is, what the changes in distance are as a function of, say, temperature. So if you're ramping up temperature, you need to take into account that third cumulant, or at least include it in the model. It might be consistent with 0, but it might be that it's important. And because it's also highly correlated with R. It's a phase term, so the third cumulant, the distance, and E0 are all correlated. So you need to get those, and then go to the phase. So those, you need to get those kind of all thought about to be able to report the distance change well. So beyond that, I would say once you've used the third cumulant, to go beyond that, then it's probably you're better off using a G of R approach, which I would say is like what is typical or similar to what the program G and XAS out of Italy, what the Chico and coworkers use. There they model G of R as a functional form and apply that to the XS instead of using a cumulant expansion. In large XS, in large FEFIT, IFEFIT, and ARGUS, what you can do is calculate a series of paths at sort of 0.05 increments and just assign a weight function to those and just turn it into a histogram problem. Where are the paths? And if I have a functional form, so log gamma, I think is what the based function is, what G and XAS uses. What are the parameters for that? There will be 2 or 3 parameters for that functional form, and that will be influence the intensity of each of those peaks and how do those add up, and that will tell you G of R. So you're stepping G of R And I think that the wisdom is that once you go beyond the third cumulon, you're better off doing that. And then you're into highly disordered systems. You're into melts and liquids.
Yeah, and one more question. It's about delta E0. Sometimes when you're feeding the spectrum measured in the same conditions and at the same beamline, feeding gives you different E0 value. So what does it mean, and should we fix it during the feeding to a single value?
Right. So I would say no to fixing it as a general rule because it's so correlated with distance that can skew the distance. But you may want to be careful that in your data processing. So so in the examples I gave earlier today, I was not careful about this at all. But you may want to be careful that as you align and look at the raw spectra and convert that to k-space, in the background subtraction, you're using a consistent value for E0 in the data processing. So the data processing will pick E0 based on the first derivative, and that is subject to noise, and it's subject to where some variation. So you may want to make sure that those are all the same for a set of data that you believe are approximately the same structure. And that way, the backgrounds will be more uniform, more consistent, and the analysis would be more consistent. The challenge is that we pick an E0 for the data in an ad hoc way based on maximum of the first derivative, and FAB picks E0 in an ad hoc based on the overlap of the muffin tins that it uses, that it poorly models. At least the XAS versions poorly model. So there's sort of two places where E0 can go wrong-ish. One of them, for the data, it can go spectacularly wrong. You want to make sure that you're consistent in what you have for the data. So other than that, I think that it shouldn't be wandering around a lot as you do fits, unless the data is noisy and you kept bad fits. Does that make sense? Or I hope that it's hard to see when I'm not looking at the questionnaire or it's the right answer to the right question. So I hope that
it sounds reasonable to me. So I would say that's the sufficiently good answer. So there's so many questions. I hear what you're answering and read the questions at the same time. So here's a question about Zanes, how muffin tin approximation affects Zanes. But I believe if Jolie is the guy who will answer this question.
I'm totally Josh, Fair, and Eves on that. Ask them.
Yeah. Right, so it's their territory, and there was another question. Let me see. Is there any threshold to decide the best models according to the residual factor, or? It's simply the lowest R, or there are some other factors that you have to look at.
Yeah, so if the lowest R factor and the lowest chi-square or reduced chi-square don't agree, then you got a question. Actually, so there are fit statistics. They were reported for some of the Zanes data too. There's these information criteria, Bayesian or Akike, that are also reported. That should also be the lowest should be the best, and if they're all consistent, that's good. If they're different, I'm not sure that anyone on the planet knows which one to pick. Probably the information criteria. In a different way, the number of free parameters and based on like maximum likelihoods affects.
You mean the F test? Yeah.
Yeah. Well, so actually, so there's these statistics that are reported. I think if I get to it, if I get to an example, they'll be reported. And those take into account, at least partially, like the log of the likelihood. So those are often used as slightly better than simply which reduced chi-square. Best reduced chi-square is what I learned a while back, last week, 20-something years ago. Reduced chi-square is like the start. And if reduced chi-square is different than R factor, I don't know what to tell you. But I would probably defer then to these Bayesian and Ikeki and if they're not consistent, you're at the noise. I think you're at the noise level where it's going to be difficult to say which of those two models is better. Honestly, I mean, you want to pick one, but if their two models are equally good, it's hard to tell the difference.
That's true. So another question is replacement in the FEF file. It generates that's the phase and amplitude to fit. But what about the coordination number?
Yeah, so I will show you this too. The FEF NNN.dat files, those include the coordination number. This can be a good thing, it can be a bad thing. And but you need to think about that at times. What I often do, and I think one of the examples I'll go through does this, I just set, in fact, you can do read the FEF.dat file, but also just set coordination number for that to be 1. That I want one of those paths, not 6, or if it was 5, 5, I want one of those. I want one of those iron oxygens, I want one of those iron chlorines. And now in the fit, I'm going to vary n, and then that will happen. So that's a good question to ask because it's a common problem. It's something that you kind of have when you start mixing paths and thinking about mixed coordination shells, you have to think about it, and you have to worry those details a little bit. Yeah.
Short question: is there an easy way to evaluate the noise level in the data with Larch?
Yes, that is done automatically. There is a function to estimate the noise level. I skipped over that part. And it's based on the high frequency part of the data. So it looks out at the data like here. You can see data to 8 angstroms. If you look at the data out to 15 angstroms, you can usually argue that there's no data there. It's not always true. And so out there is noise, and then if the data in the spectrum is white, then you can use that to fold back what the uncertainty in the data is. So we use that actually as a starting value for the noise level. It's not right, but it's not. It's only off by an order of magnitude. I'll say that. So it's the right scale-ish, and for most decent data, it's off reliably by a factor of 5 or so. So the chi-squares are more like in the 20s to hundreds than in the ones or in the millions. But it's about right. It's not terribly right. And what it's missed is the systematic errors at low R that are actually probably dominated by the poor background subtraction. So for this part of the demo, or for this part of I'm going to start on using the command line. So there is a program called Larch GUI, and that just shows. Actually, this came up. I showed this, I think, from the XAS viewer. Here, you can read in data and so on, but here it also shows all of the XAS functions that are available. So the autoback function and how to run it, and estimate noise. That's the function to estimate noise. There are functions to run FEF and so on. From here, I'm in the folder, the XAS analysis folder. I'm going to also have a shell open here just to show you here. There's a folder called FEF copper, and I have in that a FEF.input file. Okay, and I'm just going to run FEF on that file. So in here, I'm in the right folder, so I'm just going to say FEF and this is FEF6. Actually, Larch comes with both FEF6 and FEF8L, so 8 for XAS. Let's see if this works. I'm typing this live in a demo, so of course things are not going to work, but does that work? Oh yeah, it works. So that actually ran FEF. If I do, so let's see that. Those files actually got built right now. I hope. Yeah, those are from today, 12:07. Those just got run. Those files are they just happened. We just ran FEF on that set, and I'm going to run FEF now on the FEO. FEF for iron oxide. So FEF by itself, FEF6 especially, runs very quickly. It's takes longer to write it out than to run the program. Those just got run, and now I'm going to open up, and those just got run. I'm going to open up a series of files that were scripts to do the fits. So we don't have, I don't have yet a GUI for fitting. I'm on the fence about whether that's a good idea or not. And I would, if anyone has strong, suggestions or ideas on how to do that, I would be happy to hear it. We've had many discussions about this over the years, about how to do this well. And I often think that actually this technical approach is actually not so bad. So I'm going to run the fit this way. So we have this is our same iron oxide data that I've been showing earlier. I'm going to, and this is all from the command line, or you can run this either from the Larch buffer or you can make this work from Python with the right imports. It all works well. I'm reading in the raw data file with energy and the intensities from the ion chambers. I'm making mu. I'm running auto back on it to do the background subtraction. I use k-beta 2 and BKG of 0.8. Like there, that's documented. So in a lot of ways, running this from the command line like this, or using the buffer, is good because it's reproducible. You can easily, make this happen. So I'm gonna skip over this for a little while. I'll come back to it. Here, I'm going to define a path, a FEF path, with that file, the FEF001 that we just calculated. I'm going to say the degeneracy is 1. I'm just going to ignore that it thinks that there are 6 iron oxygens. I want there to be 1. And then I'm going to say the S0 squared, the amplitude parameter should be my S0 squared, which I said fixed to be false. So set it to be, fixed to be 0.75. Set it to 0.75 and don't allow it to vary in the fit. N is 6, and it will vary in the fit. So I have this set of general parameters, and then this set of path parameters. Each one is just a mathematical expression in terms of these parameter values. So I'm going to define, because we could fit in multiple spaces, we actually set it up so that we make a transform thing, object, group, whatever you want to call it. I'm going to set all the Fourier transform parameters here, k-space between 2 and 13.5, Hanning window, and they'll fit in distance between 0.9 and 2 angstroms, which is what we saw earlier, right? And then I'll create a data set, a single data set here of the data, FEO dat, that data set, a list of paths, and then how to do the Fourier transform, or how to do the transform in general. And then I'll do a fit. So that's a data set of the parameters, our parameter group, to data set. Actually, you could name these anything you want. That's how I'll do the fit. And I'm just going to run that. So that's run. And you can actually automate this as well, but I'm just going to run FEO, because I want to show this part. So I'm going to run that. I'm going to spell that out correctly and run that. And hopefully this will work because, the demo. There we go. There's a fit. And this is like exactly or similar to what I showed in the example in the slide presentation. Here's our first shell fit. There's the first shell in K-space. It doesn't look like a good fit, but it is. E0, here's our parameters, where n times S0 squared is like about 5. E0 is about -6. Our distance is actually even shorter for this data set. We refined to 2.08. And now scroll up a little bit because we have here the variables in the fit. So we have n and the S0 squared that I fixed and the parameters that I varied and their estimated uncertainties. And then we also have here up here at the top the statistics. So there's the number of variables, the number of points, the number of the appended points is 8.7. We have a chi-square and a reduced chi-square, an R factor of 0.01. And then we have these other fit statistics, both of which are around 18. And those are again useful for defined. You can check the documentation for how these are defined. It's pretty straightforward. And well-known fitting statistics that can be used. In addition, there's correlations between those two variables. And then there's a function. So we printed out that report, and then we plotted the results, and that's the result of the fit of that running that plot chi-fit function. So that's how you do fit, and I think that's like pretty much in the like similar to in the presentation, but also like that paragraph of text will do the fit. Again, when Artemis did a fit, it would allow you to manage the paths and set these up, but it was doing basically the same thing. This was what was called, this parameters was called get set def, and you had a set of functions. You had to define the Fourier transform ranges, and then you did a fit. Here we've abstracted a little better the idea of using multiple data sets. So the data sets could be, you can have a list of data sets. Each of them has a set of paths. So I guess, are there any questions about that? If not, I'll pause. If there are any questions about just doing that, the mechanics of doing that, or what it means, and then I'll go on to do the second shelf. And we'll see if we can get any further than that. So was that is doing the fitting. That's my Artemis demo. Okay, so if there are any questions, let's just make that more complicated. Let's see how complicated we can make this. I have another file that's if I can open in this thing, FEO, and again, if you download this set of files, you have all of these scripts, and this is now just a repeat of the same thing. And I've just added a few more variables. Actually, I renamed n, del r, and sigma 2 to have an _1 to signify the first path. Then I added ones for the second path. So I added 3 more variables. So I changed these definitions a little bit. And here, E0 is still the same for the 2 different paths. It's the same parameter here and here. I have the path 002 for the path for iron. The Fourier transform data information is the same, and now the path list is just a list of paths. So it's path FEO and path FE, and you can have that path list be any Python list you want, any list of paths. We'll do this again. We'll say do that fit to that data set and do the plots. And actually, we'll do another plot too in the third window. So that's the same kind of thing. And I'll just run that one and see if it works. Because, you know, it's a demo and something's bound to fail. We do the demo until things start to fail. Okay, so this looks pretty similar to what I showed in the presentation. The K fit looks a lot better. There's still stuff we're missing. The K looks a lot better. The distance, or the R space data looks much better. Now we have those two going, and we look over here at the report. Now it's a little more complicated. We have more variables reported. S0 squared is still fixed. Delta E0 is now 2 volts. We have an N that's 5.7. And so those are the fitting parameters. And then for each path, we have a path parameter. And N times S0 squared is 4.3, but that's because N1 was actually more like 5.7 plus or minus 1. So the coordination number actually comes out pretty good. It's 5.7 plus or minus 1 and 13 plus or minus 2 for the iron using this word. So, it's not so bad. The distances got better, but they're still a little on the short side. Again, I don't know if all of the iron oxygen data all the WUSTA data I ever measured has some hematite in it, but I always get a shorter distance than 2.14. We've measured this many samples. We often use this at an XAS school as one of the standards, and it always comes out that way. Maybe somebody knows. I think it's always contaminated slightly. Iron 3 plus oxide. And then here again are the two paths that go to the sum. So I just plotted back to my window here. I just plot the paths in K space. It will plot the sum, two different paths. So the iron oxygen, again, it's labeled path 1, iron oxygen, and the iron, again, this lower frequency for the shorter distance, the higher frequency for the longer distance, and peaking up in higher in K for the higher Z scatter. Any questions about this? Because I think that now we have a little bit of time, and I have maybe one more example in me, or we could just ask questions. And so I'm happy to hear any questions.
There's a question from a previous spot, if you don't mind.
Sure.
It's related to multiple scattering. So you mentioned that the change in 1/10 of angstrom, right? Should this change? The theft should be recalculated. Should be rerun to recalculate the phases and amplitudes. Do you know any tool that does this automatically?
No. No. Automatic tools to do this. So okay, there's maybe that's a no, but maybe it's a not yet. In fact, we have Bruce and I, or John, or Bruce and I, and we can include Josh and other previous XF FEF people. We have a version of FEF that is FEF8 that is available, and it's actually included in this. So actually, there's a FEF8L that we can run. Features of FEF8 that we have is that we have the shareable library to say, here's a path parameter, here are the potentials, calculate that XF contribution on the fly. That is, don't write that f001.dat file, just calculate it. Here's the path, calculate it. So we have the ability now to do those calculations, to store the potentials and the geometry of the path, and say, give me the contribution from that. So we could be refining from paths that are defined by their geometry and not by exactly their fef.dat files. We don't have this. We don't have that implemented yet, and that would eliminate this problem, because if the path distance is, it would help eliminate this problem. If the path distance got too calculated, if it gets too big, it still gets too big, you might want to redo those potential calculations. And maybe it would help a little bit and not a lot, but we could in principle do that. Redoing the potentials calculation, we really have to redo the potentials because the structure changes dramatically. I think you have to rerun, and that can take the seconds instead of the milliseconds or the microseconds to calculate the path contribution. So we don't have any of that automated yet. The tools are available. We have the FEF8 and the libraries. We've done that part. We haven't gotten into the fitting code yet. So like with a fitting GUI, if people or other complex analyses components, if people are interested in that, this is all open source and it's in Python. It's easy to work with. The code is pretty. It's in Python. So if you know Python, it's possible to do this, and it might be that you could add, some little piece or help with that. So if anyone is interested in doing that to do better fitting and more complex analysis on harder systems, we'd all be, eager and willing to help guide, with the part. That's an open invitation.
Actually,
And actually, I want to say that extends. If I can say, that extends to the MCARLS and to other things. Actually, I didn't show some machine learning components that are in the SANES part, but it also applies to any of those. We have some of those included. We don't have all of them. We're happy to include any of them, and we're happy to work with anybody on doing a better job of all parts of this. Yeah.
I just want to mention that this sort of a tool will be covered on session 4, because EVAX, developed by Yanis and his colleagues, it's doing pretty much this thing. It in a little more complicated way, because it reveals the whole structure, and then it's trying to find the best fit on every iteration. So it recalculates the whole FEF set on every iteration, which is very time consuming, but the most accurate approach. There was a question how to correctly treat the surface effects. If something is adsorbed on the surface, how to include this correctly into the feed. Like if there's a nanoparticle sitting on a surface of the substrate.
Okay. So right. So the coordination number would be lower if it's a nanoparticle on the sub, but you can. So one thing to do for something absorbed onto the surface. If I can go, see if I can go back. Okay, yeah. Let me see if I can go back. Okay, so one way. Yeah. Okay. I didn't mention that. I should have mentioned this. I often mention this. Okay, so we have this FEF.dat file, and you can edit this. So if you have, say, arsenic absorbed onto iron, you could put arsenic here at 0, or you could add an arsenic at some positive Z value, and then to make a surface, get rid of all of the other atoms with Z greater than 0, and you've made a surface you've made a 110 surface. So if you want to simulate Zorb to 110, or 111 or some other, or RCut, you can generate a surface structure and then put an atom on that structure relative to that. And that will simulate, the atomic species of interest relative to that structure. If when you do that, then you want to look into the polarization, because whether the polarization is in the plane or out of the plane makes an enormous difference. So you want to think about and include those effects, but you want to think about and include those effects when you do the measurement too. If you have a flat surface and you're looking at particles on that surface, in plane versus out of plane is very different. I hope is a start to the answer to that complicated process.
Okay, right. So another question, but to me, it's more instrument related. So sometimes two samples have the same oxidation state and the same Zanes profile, but they're the edge shift are different. Right from one measurement to another. So what does result in different E0 values? To me, it's rather the instrument error, and E0 will be different. Just correct me if I'm wrong.
I agree. If that's an effect of the monochromator calibration changing between two scans, then yeah, that will be, the E0 will be different. You may want to align the scans, and I will argue, or at least hope to you to and whatever beamline that is to try to fix the problem, because that's a problem that should be fixed. And I recognize that it's not always fixable, or that it's not easy or cheap to fix, but it might be fixable. And it's, it's better to have as reproducible as possible. And I think actually, I want to say also that I think that a lot of modern instruments, so the beamlines that were built after sort of the early 2000s, they're all much better than the ones that were built like 30, 40 years ago, where those problems were common. I think now they might even be to the point of uncommon, but you can still like correct for them. So you can add a either downstream of the sample or scatter into a foil and upstream of the sample if you can't get transmission through your sample, or measure the foil once a day. All of those work okay, and I think for a lot of beamlines, that's now like working well enough for these instrumental corrections. But I'm not certain that all of them are that way, and it's hard for the user to deal with that fact when it's not true that when there are instrumental variations.
Yeah, it's
Sorry,
the first thing. It's always the first thing to exclude, that the experiment is reliable and is giving you the reproducible data. So another question is about the fitting in multiple k-weighted spaces. Can you fit in multiple?
Yes. I didn't. The Pfeffet transform, you could just have k-weight be a list of values to fit multiple k-weights. Actually, you can also fit. There's also this is using k-space. You can fit in W wavelet space. You can fit in k-space if you want. Don't do that. It's so easy to go like off the rails when you fit in k-space because you haven't filtered completely. So, but so there are some examples in the documentation actually doing fits in wavelet space. They're harder to like wrap your head around, which is kind of awesome. It's always good to have like things that like should we just try that? I don't know if it's going to work. I was going to talk about though. There's more documentation here, right? So I think basically all the examples I showed are similar to those data sets. And actually, I was going to show if there's time. There might be if there's time or interest. This question about so I'm going to question. Yes. So yes, you can specify multiple k-weights, and it's not a bad thing to do. It's a fine thing to do. I applaud that. Zinc selenide. Okay, this is sort of a more complex. I'm just going to run this because we have. So here, question. This is a long-ish example, and it's sort of like maybe mind-blowing, but that's always a good thing to all scanners. That's always a good thing to end with. Just do that. The question, so this attempts to answer the question, how well can you distinguish different atoms? So in this example, zinc selenide data, I ran the Pfeff calculation. I ran the Pfeff calculation, doing the replacement I recommended or talked about here in this. here. Um, zinc selenide. I just created, instead of having selenium as the only neighbor atom, I added zinc as the neighboring atom, and krypton actually in a different run, I added arsenic, germanium, and gallium. So I fit with a scattering atom, not of just zinc and selenide, but of all of the different, of all the atoms plus or minus a few around selenium. So that is then in this rather complex example, I made a path for each of those and then try fitting each of them. And here's the results that I get. Actually, so that's the fit with the zinc to rubidium and so on. And then if I plot those out, you see plots. The fits aren't so bad. And then here, there's a table of scatterer. So here's using zinc as the scatterer. So zinc, not zinc selenide. And the value for the reduced chi-square, and the value for L0 squared, and then the distance achieved for that scatterer. And you can see that, well, you can almost see maybe better if it's bigger or fixed font, but the answer is selenium. But the lowest chi-square is actually bromine. Maybe arsenic is not so bad either. So it might be challenging to tell these two. But you can sort of tell that it's plus or minus 3 or 5. It's hard to tell the difference between. Like I'll just show you some of them. And it's the red curve versus the blue curve is the fit. I'll get to what the green curves are in a second. Bromine, there's selenium. Are any of these better or worse? I would say that you could probably conclude that zinc is definitely worse, and maybe zinc gallium is worse. But the other ones, like it's hard to tell. So it's selenium plus or minus a Z of 1. There's another feature that I didn't talk about at all yet, and that is we did talk about the phase shift. So here the blue curve is the data, and the red curve is the F calculation, and that F calculation includes the phase shift, right? That there's this delta. But if we know that delta, we can phase shift correct the data. So this green curve is when we that known phase shift and unapplied it to the data. It changes our Fourier transform into an optimal transform. I'll spare you some of the details. It's all possible to do in code, but it's not hard. It's just that's there. So that's the phase corrected data, and there's a question of whether that's like a better thing to show or not. I would argue that it's usually a better thing to show, but there's this theorem that, and if you look back at like the XAS equations that we have, if we were able to remove that delta, then the imaginary part of the Fourier transform would be 0 at the right distance. So there's this is a blow up of the imaginary part of the phase corrected portion of the spectrum. So where it crosses 0 should be the distance that we find. I hope that's for some. That's like, oh yeah, I understand that. So what I plotted here, or included in this table, is the distance that we refine, the 2.47 plus or minus 1, and this value of where the phase shifting, or the imaginary part, crosses 0. And those should be consistent. And if you look at the sort of selenium plus or minus 1, you can see that they're kind of close. They're within a couple of hundred angstroms. Actually, and the best one is actually arsenic. So it's interesting that the best fit for Z plus 1 and the best value of the phase correction is minus 1, whereas we know the right answer is actually selenium, because we can tell that there's no arsenic in the fluorescence data for this sample, and we believe the chemical formula for the material we bought. So that's to say, like, that's sort of like is helpful for including that Z plus or minus 3 or 5. And you might be able to do a little bit better than that. I would say here on good data where it extends out, well to 14 inverse angstroms, you might be able to say z plus or minus 1 or 2, but z plus or minus 0 is maybe not so great. Anyway, I know that example is kind of like possibly mind-blowing or advanced practice, but it's also the kind of thing you can do with these tools, right? You can just calculate what zinc gallium should be. And again, I just substituted those and reran the theft calculations, saved those files. So there's possibilities for other features. In fact, like E0 is different because the potentials are different for each of those, or E0 refined differently, actually in a systematic way. So that's also like maybe something worth looking into, I think, as you do your analyses with these tools. So I hope that was inspires more questions than I could possibly answer, but and a lot of plots of different data. So yeah. So
Okay,
yeah, any questions would be yeah.
We have a few questions about the relation between Artemis and Larch. Are the data reproducible, and what are the advantages of Larch?
Let's see. So
comparing to Artemis.
Yeah. So there's several. So there's several features that don't exist in Artemis that exist in Larch, including fitting a wavelet space. I didn't talk in much detail about statistical analyses of these. There are tools available for doing more complex exploration of confidence intervals and so on, based on the Python packages that are used. It's easier to scale to multiple. So Artemis and all of the things based on IFF have a scaling problem that they can only handle a limited number of data and depth calculations. So scaling is much better. I'm gonna say it's easier to script and to build complex analyses with. That I guess it's open for interpretation, but I think it's easier to run from. So all of these I showed was this large buffer, but those are easily translated, actually like trivially translated in Python. You just have to get basically the import state to find those functions correct, and then they'll all work as basic Python. So if you want to write any wrapper around this or any complex set of scripts to do the analysis as the data is coming in, you can do it. Whereas that's harder to do with either Artemis or IFF. Let's see, are there any other advantages? I think that for the most part, they're feature compatible, and we worked hard at making sure that they gave approximately the same results. There are places where, especially for the background subtraction, where the uncertainties are better in Larch compared to AutoBac, but I think that that's at the sort of the noise level. Yeah.
To me, having a possibility to write a script is already a huge advantage. Automate something and leave all the dirty work to the machine to calculate.
I would also say that there's a part of it that's also like it's the script aspect is self-documenting. So even if it's not, if you're using a GUI, you want that to be able to generate a script so that you have a record of what happened. But Artemis did that too. We were, yeah.
Maybe I didn't get too much into Artemis to learn how to do this.
Yeah. Okay,
so there's another question about the Zane's analysis. So usually the first derivative if you take a first derivative of the Zane's spectrum, all the features are more pronounced on the derivative. Isn't it better to use the derivative for fitting and fingerprinting?
Certainly possible to do that. It's not a bad idea. It does remove, part of the spectrum.
Normalization problems, for instance.
Yeah, and it also can emphasize some noise portions, but it's a fine thing to do. I didn't show that, but it's a fine thing to do. And the PCA and all of the linear algebra approaches work just as well on any aspect of that. And actually, the PCA, the first thing it does is get rid of the mean. So then it's all differences anyway. So, so you can definitely do that. Many people will even take the second derivative and look at that. Those are all fine things to do. I don't think that it's going to change your results a lot. It can change your sensitivity some.
Then, simple question: Why Larch? This name Larch, where did it come from?
Tree. So there's a common theme in Python packages to name programs or libraries after Monty Python packages. So that's part of it too. I like trees. Yeah, I will also say, just for everyone out there, or if you have a question, you can send me an email, or actually writing to the IFFM mailing list is a really good idea because lots of people will respond. So you'll get answers from Anatoly and Carlo and Bruce and Matthew Marcus, and that's good. So that's better because we get awesome discussions about all aspects of XF, Zane's analysis. So asking on that mailing list is just a good thing to do. And if you can get Matthew Marcus or Carlo Segre to jump in and start answering questions, then you can get some amazing discussions. We've had a lot of fun discussions, but also a lot of where everyone learned something. So many people are paying attention to that and answering questions.
Well, what's the advantage of the wavelet fitting compared to Fourier fitting? That's quite an obvious right.
I have no idea.
Well, at least it looks better. It's more visual information.
So I'm going to say I have no idea. It's a little cheeky, right? So we sort of know that because the different F amplitudes peak up in different portions of K and R space together, that you can if you can look at that intensity map in K and R map, then you can sort of tell that things are peaking up in K and R, and so that can help. But I think that there isn't enough experience out there in the world. So there are other people who are just fitting in wavelet space. I don't think there's enough experience yet to know when it's an advantage and when it's just a cool thing. I've given talks about wavelet analysis, and there are things, especially when there's multiple scattering or peaks overlapping, where things don't look quite linear in the wavelet analyses. I'm not sure that we fully understand all that, but it seems like there's things in those maps that are giving you hints that there are other things happening than just single shells overlapping in one another, but where they're actually doing interferences, which are hard to see in either just K or just R space. But in the wavelet space, you can kind of see those things happening. But I'm not sure that that's all worked out yet. So it might be a really interesting study to figure that out.
Okay. Then what is actually the question? I think you already mentioned that, but still, you have an experience in managing many data files in Larch for XAS feeding. So the question is about 50 gigabytes.
Yeah. Okay. So, well, all right. So this is something I happen actually. So okay. So we're getting close to the end, and I'm my plea for help or assistance or people being interested in things. So as I mentioned, like I'm kind of on the fence of whether the fitting part should be the FEF fitting of XAS paths should stay as text or be a GUI, because I'll just say I know that Artemis version 1 and version 2 were very hard for Bruce to write, and it's always been a question of whether they work as well as like just writing. So long ago when Bruce and I were students together, he wrote an awesome package for doing FEF fitting, all of this stuff that I just did in a text file as an Emacs like mode, which is like that's crazy, but it was awesome and it worked better than anything since. Okay, so that's just to say I don't know that, but I have been thinking about like running through these examples and actually doing more data fits to more model compounds and running more FEF calculations. What I would like to see is a database. I haven't mentioned databases yet. For some people may know that I like them very much. I would like to see a database of FEF that can be managed on the user's computer. I think we know how to do that. But then that means that the user doesn't have to do as many calculations. They get stored in a way that's easily found by the computer. And so this question of like, do I need to rerun the FEF paths can be better managed. So I think that management can be done better. For managing lots of paths, the Athena project file, which is just a zip file, or it's a zip file, it's a zip file, and it's got all of the information you need for a spectrum, for an XAS spectrum in it. That's a pretty good way to manage lots of data. When you get to 50 gigabytes, everything gets harder. And a proper database is often good. You could sort data by, beamline or edge or position or, sample name. So being able to, the known qualities of a proper database can help a lot. I don't know of anyone actually doing that for data at the gigabyte scale. We're at the kilobyte scale for model compounds, yes. For gigabytes for beamline data, I don't know, but it's worth thinking about, and it's something that I think that other people would be interested in having a solution for, like with managing FEF calculations. So that if someone's interested in doing that, or I'd be happy to discuss that with them, share some ideas, and sharing code and ideas is a fine way to work on something like that, because I think that can be helpful for lots of people. I think it would be good for the community to have those kinds of tools available.
We have a comment that such database already exists, the database of FEF calculation is materialsproject.org.
No, the materials project is a database of mapping of material structures to Zane's calculations. And I'm talking about a mapping of paths to FEF components, to the F and deltas for the extended XAS. And the materials project is all theoretical. So I hope that sounds like a criticism, and I don't mean it to be a criticism at all, but those are Zane's calculations. Some of us take data.
Thanks a lot. That was very useful, and I believe many people will return here to download that video and to follow it step by step in this play pause mode with the data they can download now.
Thanks. Did anybody have any questions they wanted me to stay after for?